So good morning to Ananda. Good morning. Please kindly confirm audio, video and screen once. Please kindly confirm audio, video and screen. Is it clear? Yeah. Fine. Okay. So let's continue with the yesterday class. What we said yesterday is to reduce the skin effect, we have to move to the stranded conductors in order to reduce the eddy current circulation. Okay. So let's take the next heading as homogeneous stranded conductor. Okay. So I'm saying in the next slide, that is homogeneous stranded conductor. Homogeneous stranded conductor. Yeah. See, the main aim of this, what we said earlier, is main aim of this conductor is to reduce the skin effect. To reduce the skin effect. Skin effect. Okay, next thing. Kindly listen. Kindly listen. See, so as we said in the yesterday class, rather than using a big solid conductor, we are going to manufacture small size of solid conductors. Small size of solid conductors, which are going to be called as generally strands. Okay. So what I can say simply is a number of smaller cross-section strands. Bunched together and twisted throughout the length of the transmission line wire in order to make the stranded conductor, we can say. Okay. So a number of definition I am saying now, a number of smaller cross section, single strands are taken, bunched together and twisted throughout the length. Okay, bunch it together and twist it throughout the length. Why we have to twist them throughout the length? In order to make the overall conductor. Because just collecting the conductors together may not stay at one place, right? To keep that as a single conductor, we have to twist throughout the length. Maybe a small level of insulation also required to be placed on the surface of each and every strand. A low level, maybe a varnish coating or a low level of insulation might be kept or may not be kept in some cases. Okay, so let us say, for example, we have the solid conductor, something like this. Solid conductor. This is a solid conductor I am saying, right? Solid conductor. So this we are going to convert into stranded conductor. Stranded conductor of smaller cross sections, something like this. So this is one strand. Okay. So I'll say next strand here, something like this. Second strand, you can say. So it's a third strand. Like this, number of strands are kept like this, one on another. Yeah. So like this, we will have the conductor. So total we have, if you count, we have 1, 2, 3, 4, 5, 6, 7 strands total. 7 strands. So it's going to be called as cross-sectional view of the stranded conductor. And not only that, all these strands are made by same material, so-called aluminum. All these strands are made by same material called as aluminum. Hence, we are going to name this conductor as all aluminum conductor, AAC. This we are going to name as AAC, all aluminum conductor. All aluminum conductor, AAC, we can say. Okay, so let me show you that practical view of this conductor first. Later on, we'll discuss some of the things about this conductor. Okay, so I'm showing in the next slide. Just I will show the practical view of this conductor. So please kindly complete. Yeah. So I'm moving to next slide. So I'll show you this. Just go through it once. This is one of the AAC conductor, you can say. This is one of the AAC conductor. So this is the internal strand. Okay, 1 and outer strands 2, 3, 4, 5, 6, 7. Like this, the conductor will look. And this was a twisting what we are making. Okay, next. Listen. How many layers we have in this one? How many layers we have in this one? See, the people will have their own way of saying about number of layers here. Some people will say strand number 1 as 1 layer. Strand number 1 as 1 layer. And 2, 3, 4, 5, 6, 7 as a second layer. Layer, I am saying. Number of strands are 7, that's okay. But number of layers will be, number 1, they will count as 1 layer. 2, 3, 4, 5, 6, 7 as a second layer. But what I can say here is, number 1, I will consider as an internal strand. Number 1, I will be considering as an internal strand. So I will be counting up only 2, 3, 4, 5, 6, 7 as a layer. So in my view, I am going to say it's a 1 layer AAC conductor. 1 layer AAC conductor. Okay, 1 layer AAC conductor without counting the internal strand as a layer. Okay, without counting internal strand as a layer. Internal strand as a layer. Okay, so this term we should be very clear. Okay, one simple question here is, why we have to keep only 6 strands in the first layer? If you count up the number of strands in the first layer here, 2, 3, 4, 5, 6, 7 means total 6 we have. Why we have to keep only 6? Why can't we keep 7? Why can't we go for 8? Or why can't we go for 9? What we call 5? Why you are going with only 6 number of strands in the first layer means, in order to make the overall shape of the conductor in the form of circle. Okay, so you have to select the number of strands in the first layer in such a way that the overall shape, overall cross section of the conductor should come in the manner of circular. This should be in the circular cross section manner. It should be in the circular cross section manner. Okay, yeah, done. Next thing. Let us see. Mechanical strength of this conductor is very, very low. That's one of the disadvantage of this conductor, what we can feel. Mechanical strength, or we can say sometimes as tensile strength of this conductor is very, very low. So I'm saying that thing. Mechanical strength is low for this conductor. Compare it to solid. Mechanical strength and tensile strength. Tensile strength of AAC is low. Compare it to solid. See, in one way we can say it's a disadvantage. In one way we can say it's an advantage also. Say disadvantage we will talk later. What's the advantage of having low mechanical strength means? Rolling that conductor will be easy. By that way, we can transport that conductor as easy from comparing to the installation place. Okay, so rolling of that conductor will be easy on a what we call on a wheel, so that we can transport that conductor easily from company to installation place, right? For example, if the conductor is having high mechanical strength, if you want to make a conductor roll, that circle size will come very big. If the mechanical strength is high, that circle size will come very big, so that the transportation may be a bit difficult, what we are suggesting. Okay, so AAC conductor, I can say AAC conductor, rolling is easy. So I can say transportation is easy. Transportation is easy. One more thing. How is the surface of AAC conductor? What you are expecting? Is it a smooth surface or uneven surface? How is the surface of AAC conductor? Could you please tell me? Is it a smooth surface or uneven? Uneven surface, right? Uneven surface. Because of that uneven surface, definitely, we can expect that the corona may be a bit more. Corona will be a bit more on this conductor, as compared to the solid conductor. Okay, so surface is not smooth. Surface is not smooth. There are some semicircles formed, semicircles on the surface, not smooth. So I can say corona will be a bit more. Corona will be more on this conductor. Corona will be more on this conductor. Okay, next thing. What do you mean by this term tensile strength here? What's the meaning of the tensile strength? Tell me, anybody, what do you mean by tensile strength actually? So simply, if you are attempting to connect a wire or a conductor or whatever it is, a thread also you can say, if you are attempting to connect that in between two towers or two fixed points, between two fixed points, you want to stretch a wire or stretch a thread, that wire is going to experience some tension. The wire is going to experience some tension between the two fixed points. That we are going to name it as generally tensile strength. Tensile strength. Very simple word. Tensile strength is a stress. Experienced by the conductor if you stretch that between two fixed points. Okay. Now, are you stretching the power conductor between any two fixed points? Yes. Where between two towers we are stretching. So in between the two towers, the conductor is going to experience some definite amount of tension. We'll discuss about that. And if the tensile strength is low, what's the disadvantage we are going to get? That we are going to continue now. Okay? Yeah. So let's move to the next slide. So I'm taking up as an example here. For example, I'll take a ground surface, something like this. It's a ground surface. Earth, or you can say ground surface here. Ground surface. See, let me assume that we have two towers, one beside the other on the ground surface. Maybe at a distance of 100 meters or 200 meters, we have two towers. So I'm showing the two towers now. This is a tower number 1. Something like this. Okay. So I'll show tower number 2. Tower number 2. Like this. So these are the two towers here. Just listen my words. Very simple thing only. Tower number 1, tower number 2. Now we are attempting to keep the conductor between two towers. These two towers. But you see, whenever we want to keep a conductor between these two, I'll take one fictitious line, imaginary line first, as a line joining the tower tips. I'm going to take up one fictitious line. Just observe that what I am showing now. It's one of the fictitious line joining the tower tips like this. Simply line joining the tower tips we'll call. Line joining the tower tips. Joining the tower tips. Okay. Next thing. See, our aim is to keep the conductor along with the line joining the tower tips. Along with the line joining the tower tips, we have to keep the conductor, but it is not possible. Definitely, even though you stretch that as much as possible, but still it is not possible to attach that dotted line what we have shown. Definitely, the conductor kept in between these two towers might take a path something like this. Might take a path something in that manner what we have drawn. So it is a path taken by the conductor kept between two towers. Path taken by conductor kept in between two towers. Okay. So how that path looks to be for us? How that path looks to be for us, right? This path is going to be called as catenary path. This path is going to be called as catenary path. Catenary curve, or you can say that's a catenary path. Simply, the path taken by the conductor between any two towers is going to be called as catenary path. Okay, next thing. For example, if you have unequal heights of towers, one is of larger height, other one is of lower height. For example, if you have something like this, let us say, so it's a ground surface, you assume if you want, right? So I'm showing, so this is a lower height of the tower, you can say, and I'm showing one more tower here, right? It is of larger height of the tower, something like this here, right? One is of low height, other one is of larger height. Now, if you are attempting to keep the conductor between these two, definitely the conductor may not take a straight line path. The conductor may take a path something like this. And this path is also going to be called as catenary path only. Catenary path, right? So this also going to be called as catenary path. Okay, next thing. It's not parabola. It will be called as a catenary path. Catenary path. Okay. Yeah. Next thing. Let's continue with this. Listen. Generally, at what point the conductor will experience more tension? Generally, at what point the conductor is going to experience more tension? Means generally at the tower tips. At the tower tips, the conductor is going to experience more tension. Maybe at this tower tip, it is experiencing a tension of T1. At this tower tip, it is experiencing a tension of T2. Similarly, for the unequal heights of towers also, at this point, it will experience a tension of T1, and at this point, it's T2. Tell me, please, in this unequal heights of towers, at what tower tip the tension will be more? At what tower tip the tension will be more? Is it at lower height of tower or higher height of tower? Definitely higher height of tower. We can say the tension will be more. Tension will be more at the tallest tower tip. T2 will be greater compared to T1. Whereas for equal heights of towers, I can say tensions will be equal. T1 and T2 will be equal here. T1 and T2 values will be equal. Okay. Yeah. Next thing. So let me continue with this diagram little bit. Simple. See, there is a gap between the expected line and the conductor. There is a gap between the fictitious or expected line and conductor. This gap we are going to name it as mechanical sag. Okay. And remaining height of the conductor from bottom of conductor to the ground. That remaining height is going to be called as ground clearance. H we are going to name as ground clearance. And this is going to be called as sag, and this is called as ground clearance. Let me tell you one more term here. Distance between any two successive towers. Is going to be called as a span length. Span length. Distance between any two successive towers is going to be called as span length. Span length. Okay. So this is little about the mechanical construction of line, sag, ground clearance, span length and all. Okay, let me tell you this. For example, if the tensile strength of the conductor is very low, tensile strength of the conductor is very low, we can't stretch that conductor as much as possible. We can't stretch that conductor as much as possible. Definitely the gap what we have, so-called sag, the sag value become high. So we can feel that the sag will be inversely proportional to tensile strength of the conductor. Sag will be inversely proportional to tensile strength of the conductor. Sag will be inversely proportional to tensile strength of the conductor. Sag inversely proportional to tensile strength of the conductor. Clear? Now, particularly if you think about our all aluminum conductor, for AAC conductor, tensile strength is a low value. AAC conductor, tensile strength is low value. What will happen if the tensile strength is low value? We know sag will be more. Tensile strength is low in the sense, definitely sag will be more. Sag will be more. If sag is more, what we can say? Sag is more in the sense, in this diagram, you can see the conductor is coming close to ground. So ground clearance will be less. Ground clearance will be less. Ground clearance will be less. As if the ground clearance is low, I can say definitely safety of the system will be less here. Safety of the system will be less. Safety of the system will be less. This is a problem what we are facing if you are going with the AAC conductor. Actually, we are moving from solid conductor to AAC conductor in order to reduce the skin effect. In order to reduce the skin effect. Okay, skin effect will not come zero. Listen please, listen please. By coming from solid conductor to AAC, definitely there is a skin effect, but the skin effect will be less compared to solid. But additionally, we are getting a problem of this more sag and low ground clearance. So this problem we have to avoid. This problem we have to avoid. Means we have to think in an aspect of to increase the safety of the system. To increase the safety of the system, or you can say to increase the ground clearance. To increase the ground clearance. What are the various necessary steps we have to take? What are the various necessary steps we have to take? Yeah, tell me please. What is what are the steps we can take now? One method what we can say is to increase the ground clearance. To increase this ground clearance, go for larger heights of towers. Go for larger heights of towers. Definitely this H value is going to be increased. But increasing tower height definitely increases the cost of the system. That may not be economical. Okay, so let me write. First method, first technique is increase tower height. Increase the tower height itself. Tower height. But it is not economical. It is not economical to go for higher heights of towers. Okay, next method. Next method is reduce the sag. Keep the tower height same. Keep the tower height as it is. Minimize the sag. Minimize the sag. So definitely ground clearance will go high. Okay. So reduce the sag is another option. Reduce the sag. Then who will decide the sag? One is a tensile strength of conductor. So already we have said one statement that sag is inversely proportional to tensile strength of the conductor. Sag is inversely proportional to tensile strength of the conductor. Tensile strength of the conductor. So in order to reduce the sag value, one option what we are saying is increase the tensile strength. increase the tensile strength of the conductor, or you can say increase the mechanical strength of the conductor. By that way, definitely we can stretch that conductor as much as possible so that the sag is going to be reduced. That's one technique. The other technique I am saying from formula. I am saying this from formula. Look here. Sag is directly proportional to span length square. Sag is directly proportional to span length square. So in order to reduce the sag value, it is suggested to go for lower span lengths. It is suggested to go for the lower span length. So if you reduce the span length, definitely sag value is going to be reduced. But problem is, if you are reducing the distance between two towers, definitely number of towers required in the transmission line run will be more, and obviously cost of the system is going to be increased, we can see. Okay, so I think all of you getting this point, all of you clear about this? Please tell me. Sag is proportional to span length square. By means of this, what we are saying is number of towers required will be large, required will be high. So it is also not economical. That's also not economical. Okay, so what's the method we have to suggest now ultimately? Ultimately, you have to increase the tensile strength only. There is no other option to you in order to reduce the sag as well as to increase the ground clearance. So only this method we have to suggest. Okay, tell me now, how to increase the tensile strength of the conductor? Sushma, it is coming from derivation which we are not discussing here. Sag is proportional to span length square will come from the derivation which we are not discussing. Only we are taking up only the points whichever it is required. That's it. Yeah. Next. Listen now. Listen, please. How to increase the tensile strength of conductor? Means, listen here. For example, if it's a AAC conductor we have now, it's a AAC conductor. Try to replace, listen my words, try to replace some of the aluminum strand, maybe 1, 2, 3, 4, 5, 6, 7, anything. Any one of the aluminum strand with a new strand, having higher mechanical strength. By that way, overall tensile strength is going to be increased, and we can say the sag is going to be definitely reduced. See, some of the aluminum strand we have to replace with a new strand of new material. Definitely new material means we will be using 2 or more number of materials for the manufacturing of the conductor now, stranded conductor. That we are going to name as composite stranded conductor. Okay, so let me write that. So to meet this requirement, I will be going with the composite stranded conductor. Composite stranded conductor will be used in order to increase the tensile strength of the conductor. Okay, so I will be taking up in the next slide as a heading, that is composite stranded conductor. Yeah. So here I am writing composite stranded conductor. Yeah. Composite stranded conductor. So the aim of this conductor, aim of this conductor is to increase tensile strength, or you can say to reduce the sag, to increase the tensile strength of the conductor, or you can say to reduce the sag. So definition I am writing now, definition, right? Which aluminum strand we have to replace with a new one? Could you please suggest that? It's a AAC conductor we have, na? It's a AAC conductor we have, right? Let's copy this. It's a AAC conductor, na? Which one? Which one you want to replace with a new strand? Anybody? central. We suggest to go for central. Why we have to go for only central? Why we have to replace this number 1 with a new strand with higher tensile strength? Why can't we replace number 2? Why can't we replace number 3? Why can't we replace number 4, 5, 6, 7? Why you are concentrating only central strand to replace with a new one? To provide a sort of mechanical balance in the conductor. To provide a sort of mechanical balance in the conductor, we should replace only internal strand with a new one. For example, number 2 you replace. Number 2 will lie on the top up to some length. After certain length, it may twist right, it may come down, or it may come down. So in that way, mechanical balance may not be achieved if you are going for 2, 3, 4, 5, 6, 7. So if you go with number 1, mechanical balance is also going to be maintained. And not only that, according to skin effect, again, listen to my words. According to skin effect, this number 1 may not carry a considerable amount of current. Number 1, internal strand inside the conductor may not carry a considerable amount of current. That's why I'm replacing that with the new strand. Okay, so let me write that statement. The internal strands of AAC replaced with internal aluminum strands of AAC replaced with new strands having higher mechanical strength, such that the overall strength of the conductor is going to be increased. Okay, so whatever the number 1 we have here, this number 1 is a new strand we are naming a new strand, and outer whatever we have, these are of aluminum. Which material will take? For the new strand? Anybody? So we have various materials. Let me write them. So we can go with the copper, we can go with iron, we can go with steel. These are the materials we are saying now. For the internal strand or new strand, I am saying some materials here. Copper, iron, steel. Which one? Can we use copper? No. We can't use copper because of its cost. Because if it's cost, it's not suggestible. Iron can we use? No. Rusting problem will be there. Rusting, or you can say corrosion problem will be there. So I can't go with iron. So we can go with steel. Not only simple steel, we should go with a galvanized steel. As a internal strand now. Okay. So new strand is made by a material called as galvanized steel. Now, after replacing that internal strand with the steel, listen. This conductor we are going to name it as, it's a basically aluminum conductor. It's basically an aluminum conductor with steel kept at the central. So it's an aluminum conductor, steel reinforced. This is a word what we are going to use for this conductor. Okay. So shortly it is going to be called as ACSR conductor. It's going to be called as ACSR conductor. So I am writing that name here, ACSR. Aluminum conductor, steel reinforced. Else you can call it as steel reinforced aluminum conductor also. Same thing, you can name it as steel reinforced aluminum conductor. In this way also you can write this. ACSR conductor. Copper is of costly. That's why we are not going with copper. Copper is of costly. So we are not going with that. ACSR conductor. Okay, let me extend with respect to this one. ACSR conductor, which is a very practical conductor what we are using in the present days for overhead transmission lines. Yeah, Look here. First one, just listen to my words, what I am saying you. So I have one aluminum conductor like this. Aluminum, only solid conductor, single conductor also. It's aluminum. Okay. I am showing one steel also. Steel wire. You feel it's a steel wire, simply steel wire. So I'll call it's aluminum wire. And this red color one is a steel wire. These two are in parallel. These two are in parallel like this. Connected in parallel, you see. Connected in parallel. And one side we keep one voltage source, other side we keep a load. Okay. Just look at this. This side we are keeping one voltage source like this, and this side we are keeping a load. Just look at my words, what I am saying you. Very simple one. Very simple one. Just listen. See, for example, this load is taking a current of I. That load is taking a current of I. See, the current I, whatever it is drawn by the load, whatever it is drawn by the load, definitely divided between these two, right? That current I will be divided between these two, aluminum and steel. Correct. Tell me now, aluminum will have some resistivity as rho aluminum. Steel is having a resistivity of rho steel. See, steel is a good conductor of electricity. Steel is a good conductor of electricity, but resistivity of steel is higher compared to aluminum. Resistivity of steel is higher compared to aluminum. That's a point what you have to understand now. So I'm writing now. Steel resistivity is very high compared to aluminum resistivity. If that's the case, in this current I, major portion will be carried by the aluminum wire. Major portion, maybe 90% of current is in the aluminum wire. Remaining 10% of current will be carried in the steel wire. Will you accept it or not? All of you, please tell me. Aluminum wire will carry major portion of current and steel wire may not carry a major portion of current. Okay. Now listen to me. I am adding one more aluminum wire in parallel with the existing. One more aluminum wire I have added. Then what will happen to the steel wire current? It will further decrease, na? Steel wire current further decreases because two aluminum wires are in parallel. Major portion of current was diverted onto those two. Steel wire will carry negligible amount of current. Like that, I am adding number of aluminum wires in parallel. Along with that steel, so that in this particular configuration, how is the steel wire current? How is the steel wire current to be expected? Anybody tell me, please? How is the steel wire current? Negligibly small, and ultimately we can expect that this current may be very, very close to zero. Very, very close to zero, and the total current might be flowing only in the aluminum strands. So my intention is to tell you, particularly if you talk about ACSR conductor in this manner, 6 aluminum wires, 1 steel wire in parallel. 6 aluminum wires and 1 steel wire in parallel. That steel wire may not carry any amount of current. Complete current is concentrated only in the aluminum wires. So the steel strand what we have now is going to give only mechanical support. Only mechanical support. Okay. So this new strand what we are keeping now gives only mechanical support. And it may not carry any current. Total current is getting concentrated in the aluminum wires only. Okay. So I think you are clear about this point. So next point we are going to discuss about this. Next one. Let's move. Yeah. So let's say small d It's a diameter of each and every strand in the stranded conductor. Okay, diameter of each strand. All the strands are identical in shape. All strands are identical in shape. Identical in size. All strands are identical in size. Diameter of each strand. Next, capital D. So diameter of ACSR conductor. Diameter of ACSR conductor. Diameter of ACSR conductor. Okay. Next, for example, if it's a one layer conductor, what we are talking about? One layer conductor. Okay, before moving to this also, just listen to my words. Before moving to this discussion, I want to tell one more small concept here. Just look at this. I will write. I'll write here. Just listen. How many layers we have here? One layer, right? One layer. How many strands we have in that layer? 6. First layer is having 6 strands. For example, if you have second layer, how many strands you have in the second layer? Tell me, please. How many strands we have in the second layer? Expect that number. It will be 12. It will be 12. And if you have one more layer, how many strands you can expect now? 18, you can see. 12 plus 6, that will be 18. If you have one more layer, then it will be 18 plus 6, that will be 24. Like that, the number of strands will increase as and when the layer size is increasing. Number of strands will increase as and when the layer size is increasing. Okay, such that the overall shape of the conductor is circular and each and every strand is having of identical size. Identical size. Okay, so I'll write that. Then we will go for that diameter now. Yeah, so let's take as number of layers increases. Number of layers increases. Yeah. So internal strand 1 we can say first. Internal strand is 1. First layer is having how many strands? 6. First layer is having 6. Second layer 12. Third layer 18. Fourth layer 24. Next it will be 30. Next 36 and so on. Like this it will be. So first layer consisting 6 strands. Second layer 12. Third layer 18. Fourth layer 24. Like this, the number of strands will increase. In bracket, number of strands increment. Strands will be in this order. Okay. Yeah, all the discussion, whatever we are making now, that we are saying without counting internal strand as a layer. We are not counting internal strand as a layer. Right? Outer layers only we are counting as number of layers. That's the meaning. Okay, let's move ahead to the present discussion what we are making. Small d we considered as a diameter of each strand. Capital D is a diameter of ACSR. For example, it's a one layer conductor. Na? It's a one layer conductor. And what's the overall diameter of this conductor to be expected now? What is the overall diameter of this conductor to be expected? So this is D internal strand and this is D outer strand and this is also D outer strand. What's the total now? Total it will be 3 times of small d, we can say. 3 times of small d. Okay. So I can say one layer ACSR conductor will have a diameter of 3 times of small d. So I think it is acceptable to all. 3 times of small d. Capital D, Sivateja, capital D is a diameter of overall conductor. How much is that in terms of small d? That's the question. Okay. So for example, if you have 2 layers, what will happen? 2 layer ACSR, how much is the diameter we can expect now? 2 layer ACSR. See, Sir, only internal is made of steel irrespective of number of layers. Yeah, Voshmita, that depends. That depends. I will come to your doubt. I will come to your doubt. Please kindly follow this. See, if you have one more layer, what will happen is one more strand will be added at this place. One more strand will be added at this place. So that this D and D will be added to the 3D. So total will come to be 5. Total will come to be 5 times of small d. So it's a 5 times of small d. And if one more layer has been increased, 3 layer ACSR, then it will come to be 70. 3 layer ACSR, it will come to be 70. 7 times of small d. And if you have n layers, what will happen? N layers, what will happen? N layers. It may come like 2n plus 1 into small d. It will come like 2n plus 1 into small d. Okay? Yeah. So just listen to these 3D thing, what I'm saying now. 2 into 1 plus 1 into small d, 3D, 5. 2 into 2, 4 plus 1, 5 times of d, 7. 2 into 3, 6. 6 plus 1, 7 times of d. So that 1, 2, 3 are layers. Layers, number of layers. 2 into 1 plus 1, 2 into 2 plus 1, 2 into 3 plus 1. Okay. And n layers in the sense, obviously it is 2 into n plus 1 multiplied with 3. Okay. So again, you say here, n is a number of layers without counting internal strand as a layer. N will be number of layers without counting internal strand as a layer. As a layer. Okay. Yeah. Next. Next thing. See, generally this ACSR conductor, what we are discussing now, it is going to be represented in a standard notation. Standard notation, I will show you in the next slide. Please complete it quickly. Yeah, so I think okay. Generally, look here. Generally, ACSR represented as a ratio x by y. ACSR conductor is going to be represented as a ratio x by y, where x is a number of aluminum strands, or you can say number of steel strands. Number of aluminum strands or number of steel strands. Okay. Y will be number of steel strands, or you can say number of aluminum strands. Number of steel or number of aluminum strands. So alternately, for example, if X is saying aluminum, Y will tell about steel. If X is saying steel, Y will tell about aluminum. That's a way of understanding. Okay, if one number says aluminum, other number will say definitely steel. For example, if some ratio is given to you, some numbers are given to you, which number you should say aluminum and which number you should say steel generally? Tell me please, if some numbers are given to you, which number you should say steel, which number you should say aluminum? Whichever is higher in number, that will be aluminum, and lower in number will be steel. So practically for ACSR power conductor, ACSR power conductors, number of aluminum strands will be greater compared to number of steel strands. Number of aluminum strands will be greater compared to number of steel strands. Yeah, okay. Now I'll take up some examples with respect to ACSR conductors quickly. Examples of ACSR conductors I am taking up. So some examples. First one, ACSR 6/1, or you can call this one ACSR 1/6 also. ACSR 6/1, or you can say ACSR 1/6. What is that 1 and 6 here? What is that number 1 and number 6? Whichever is lower in number, so-called 1, it will be steel. And higher in number 6, it will be aluminum. 1 steel strand, 6 aluminum strands. 1 steel strand and 6 aluminum strands. Okay, how many layers we have? That's what the conductor what we have shown here. Yes or no? So it will be this conductor only, this conductor only. How many layers? Only 1 layer. Only 1 layer. 1 layer. And what's the value of capital D now? 2n plus 1 into small d. 2n plus 1 into small d. So it will be 3 times of small d, you can say. 3 times of small d. That's the first one. And the second example. ACSR 30/7, or you can say 7/30 also. ACSR 30/7, or you can say 7/30 also. Now in this ratio, whichever is lower in number, that is 7. 7 will be steel, 30 will be aluminum. Okay. 7 will be steel. Steel strands, you can write if you want, steel strands elaborately. 30 will be aluminum strands. 7 will be steel strands and 30 will be aluminum strands. How many layers you can have now? Guess. Number of layers, how many you can expect in this? How many number of layers? Just listen to my words. See, 7, say first internal, what we have to keep? Internal will be steel. On the surface of steel, we should build up aluminum. Internal will be steel. On the surface of that, we should keep aluminum. So 7 steel we should take first. 7 steel. Just look at this series, what we have shown. This series. Number 1, I will consider definitely steel. Number 1, definitely I will take steel. But how many steel required here? 7 required. 7 required in the sense 1 and 6. Both will keep steel. 1, 6. Both will keep steel. So that 1 plus 6, 7 steel completed. 7 steel completed. On the surface of that, we should keep 30 aluminum. 30 aluminum. So let's say 12. 12 aluminum I kept, but required aluminum is 30. So one more layer I should keep. So called this 18 also I will keep aluminum. Then what's the total aluminum now? That will be 12 plus 18, 30. That's sufficient. So internal 1 steel, next 6 steel, next 12 aluminum, next 18 aluminum. That makes the resultant conductor what we have given. See, my intention is to tell you whatever the 30 I said now, 30. It's not the number of aluminum strands in the last layer. It's not the number of aluminum strands in the last layer. It will be the total number of aluminum strands. Total number of aluminum strands. So steel will be 1 plus 6 and aluminum will be 12 plus 18. So the number of layers will be 3. 3 layers, and overall diameter will be 2 into 3 plus 1 times of small d. So it will be 7d, we can say. Will be 7. 7 times of small d. So I think all of you getting this? Clear? So total, how many layers we have? 1 layer steel and 2 layers of aluminum. That's it. Next, one more example I'll take, third one. ACSR 54/7. Or you can say 7/54. ACSR 54/7, or you can say 7/54. 3 layers. This is the thing what you have to count. 6 first layer, 12 second layer, third layer 18. How many layers you have? Only 3 layers. And an internal strand of 1. That's it. So let's continue. So ACSR 54/7. ACSR, how to count layer? Just now I have explained. How many layers we have? 54/7 or 7/54. Steel, 7 we have, 7 strands, and remaining will be aluminum, 54. 54 aluminum. Steel, that 7 will be 1 plus 6, you can say. And 54, how we can get? 12 aluminum, 18 aluminum, 24 aluminum. 30 plus 24, that will be say 54. And then 7. So how many layers we have? 6. Layer number 1, 12. Layer 2, layer 3, layer 4. So number of layers will be 4. Okay. So capital D will be 2 into 4 plus 1 times of small d. So it will come to be 9d. 9 times of small d. Yeah. So now I will try to show you that practical data sheet of these ACSR conductors. Just look at in the next slide. So with the courtesy of AP Transco, we are displaying this slide. Just go through this one. Go through this. You can see the levels of voltage here: 130 kV, 220 kV, 400 kV. 132, 220, 400 kV. Span lengths are given here. Span lengths 320 meters, 350, 370, 400 meters. Distance between the successive towers. Okay. Next, you can see here conductor. First one for 130 kV. Look here, please. Look here for 130 kV. 30 plus 7 by 300. Not 300. It is 3.00 actually. There was a printing mistake. 3.00. There is a diameter of each strand. 3.00. 30 plus 7. So it's a ACSR conductor consisting 30 aluminum, 7 steel. That's the meaning. Okay. Next for 220 kV, 54 plus 7. 54 aluminum, 7 steel. Okay. Next here also 400 kV, 54 plus 7. Okay. 7 steel, 54 aluminum. And one more thing, what you have to observe here is earth wire. It's a term like HTGS, high tension galvanized steel. High tension galvanized steel wire. It's also a stranded conductor of 7 strands. Each strand diameter is 3.15 millimeters. 3.15 millimeters is each strand diameter. Yeah, all of you getting this table, what I'm saying? N is the number of layers without counting internal strand. Now, why you have considered? We have not considered Bhavani. I have not counted that number 1 as a layer. Not counted number 1 as a layer. Yeah. Look here, these names of the conductors, how they have given. One is a panther. Next one is moose, zebra, moose. What are these names actually? This panther, moose, zebra, these are animal names. Animal names. Okay. Representation is different here in table. What is the difference you have, Akshay? Akshay, what's the difference you got here? Huh? Just look at the thing what I said. 54 by 7 I said, but they have given in a clear way. 30 plus 7 they have given. What's the mistake in that? Huh? 54 by 7 I said, but here they said 54 plus 7. What's the mistake in that? Yeah, kindly listen. See, these conductors are denoted with animal names. Conductors are denoted with the animal names for a easy identification. Easy identification. Maybe if you compare the moose and zebra, zebra may be of smaller size compared to moose. Moose is a bigger size animal. and zebra is a smaller size animal. So if somebody says that it's a conductor of moose, it's a conductor of zebra, you should say that zebra conductor size will be less compared to the moose conductor size. That for that identification they are given. For example, if somebody says the panther conductor and zebra, so panther is of smaller size compared to zebra. So maybe that panther conductor, what they said, is of smaller size and zebra is of the larger size. That's a comparison. For easiness in the comparison, right, which is of smaller conductor and which is of larger size conductor, they are denoting the what we call conductors with the animal names. Animal names. Okay. So for easy identification, you can say. Okay. 3.53 is a diameter. 3.53 is a diameter in millimeters. Diameter in millimeters. Yeah. Small d, diameter of each strand. Small d, diameter of each strand. 3.0, 3.53, 3.18, these are diameters of each strands in millimeters. I have answered just now, Vinita. Check that. See, actually, at where they said 7 by 3.15 in the sense, we have 7 strands. 7 strands. It's also a stranded conductor, but all the strands are made by same material, that is steel. That is steel. Each strand diameter is 3.15 millimeters. 3.15 millimeters. Okay. Yeah, clearances and all you can go. Clearance and all you can go. So next, let me move ahead. Earthwire I have explained just now. Moose is an animal name, I said already. Moose, zebra, these are animal names. Yeah. Look here. For example, we have one conductor, something like this. Just observe now. This is these are steel. These are steel. Okay, so total 7 strands of steel. And before keeping aluminum on this, one, I'm maintaining some gap. After keeping that gap, so I will be keeping some circular shape. I will take first, so that I will show the strands also. Like this we have. Okay. So outer strands are aluminum only. All these strands, whatever I am showing here, these are of aluminum. Just listen to the words. These are aluminum and internal will be steel. In between these two, steel layers and aluminum layers, we are filling with some low-grade insulator material. It's a filler material we'll call sometimes. We call as a filler material. Filler. Okay. That that light green, what I've shown there, it's a filler material and it's of low-grade insulator. Low-grade insulator. It may be Hessian material sometimes or jute. Hessian or jute, you can say. Yeah. Hessian or jute. So definitely, it's an ACSR conductor. Yeah, tell me please. It's definitely an ACSR conductor. Yes or no? Definitely, it's an ACSR conductor. but we have a filler material between the steel and aluminum layers. In steel and aluminum layers, we have a filler material. And this conductor, we are going to name it as expanded ACSR conductor. ACSR conductor only, but with of larger size. Okay. So this name you can say as expanded ACSR conductor. Expanded ACSR conductor. Expanded ACSR conductor. Okay. So the main aim or main advantage of this expanded ACSR conductor is overall size of the conductor was increased. Overall radius of the conductor was increased. What will happen if the overall radius was increased here? Overall radius of conductor was increased. What's the advantage of getting this one? You know, electric field intensity is inversely proportional to radius. If radius is more, field intensity is less. Corona reduces with the help of this conductor. The use of this conductor, we can say corona is going to be reduced. That's the advantage. That's the advantage. Okay. Expanded ACSR conductors are used to reduce the corona. Okay. Next, I'll tell one more conductor before moving to the next chapter. One more conductor I'll tell you. So next, look here. So I'm taking up one small circle. Yeah. Just have a look at this one, what I'm showing. See, we are keeping conductors. We are keeping conductors or strands, you can say, strands on this circle, something like this. Okay. So these are a number of strands, what I'm going to show now. So like this you have. So it is almost like a hollow conductor, right? Number of strands are touching together and we are keeping that in a circle. But inside the circle, we don't have anything. Inside that circle, we don't have anything. Comes in this manner, right? So it's a hollow conductor. Basically, it's a hollow conductor. But to have that support means to make all the strands in that shape what we have shown. To make all the strands in that shape what we have shown, we used to keep some arrangements, something like this. Some strip kinds of arrangements we are going to keep in such a way that all the strands are kept in the form of circle as we have shown on the figure. Okay, so it's a hollow stranded conductor we can call. It's a hollow conductor, but it's a stranded. So hollow stranded conductor. Stranded conductor. And this is going to be called most of the times as anaconda conductor. It will be called as anaconda conductor. So it was made by Anaconda Wire and Cable Company in United States, right? Anaconda Wire and Cable Company in the United States. It's also an animal name, indicating that this conductor size is of large size. Anaconda, in the sense, it's a very bigger size. That's the meaning. Okay. So anaconda conductor, and this is used in United States for the EHV and UHV lines, particularly to reduce corona. The main aim of introducing this conductor is to reduce corona. Corona reduction is the aim of this conductor. Corona reduction is the aim of this conductor. Okay. Yeah. So till now we have discussed about different types of conductors. No steel here. Inside it's air. Yeah. Next, listen please. Listen. Let's concentrate only on the types of conductors what we have listed there. That is solid, AAC, ACSR. We'll think about only these three now. We'll think about only these three. Remaining two conductors we have discussed. One is of anaconda conductor to reduce corona. And the previous one, so-called expanded ACSR, also to reduce the corona. Keep it aside. Keep it aside. Let me give some conclusion, small conclusion for you regarding the conductors what we have discussed till now. Solid. Next one is of all aluminum conductor. Next one is of ACSR conductor. Keep the last two conductors aside. Think about only these three. Think about only these. Yeah. Very simple conclusion I'm going to give. Red strips are mechanical support. Red strips are mechanical support. Mechanical support. Okay. Yeah. Listen, please. Listen. Why we are moving from solid to AAC? Why we are moving from solid to AAC? In order to reduce the skin effect. But skin effect will not come zero. After going to AAC, skin effect will not come zero. Definitely there is a skin effect, but it's less. Okay, fine. But what is the problem of AAC? Transportation is easy, but sag is more. Stretching the conductor is difficult, so sag will be more. If the sag is more, to reduce that sag, to increase the mechanical strength, we are moving from AAC to ACSR. So ultimately, for AC transmission lines, what we are seeing outside, we will be going to the ACSR conductor. Okay, so let me write. So ACSR conductor is used in HVAC power transmission. HVAC power transmission. Okay, and what about for HVDC transmission? What about for HVDC transmission? Anybody tell me, please? HVDC transmission. Which conductor will use? Can we use solid? Yes, you can go with solid because HVDC in the sense we don't have an issue of skin effect. We don't have an issue of skin effect. That may be the reason why you suggest to go for solid. But what's the problem of solid? Tensile strength is very high. Transportation is very difficult. Transportation of solid conductor is very difficult. So to make the transportation as easy, you might be shifting from solid to AAC. Solid to AAC. Okay, we came to AAC. After coming to this AAC, the problem is again sag is more. Problem is sag is more. To reduce the sag, we have to move to again ACSR conductor. So my intention is to tell you, even for HVDC power transmission, we have to go with the ACSR conductor only in order to have an easy transportation as well as less amount of sag. Okay, so this is used in HVDC power transmission also. HVDC power transmission also. Okay, then could you please tell me what is a practical application of the solid? Yeah, what's a practical application of solid? Tell me please. And practical application of AAC. What's the practical application of these two? AAC where will use? Maybe in the service mains, maybe the cable, underground cables you can see sometimes. UG cables, because you don't have a phenomena of sag there, that's why we might be going for what we call AAC conductors there. Underground cables, better I will. UG cables and house wiring, we are using copper. But still I will keep the house wiring in the same category of homogeneous stranded conductor. House wiring. For example, if you cut the house wire or silk wire, will you observe only one strand or number of strands there? Definitely number of strands in order to reduce the skin effect. So definitely that homogeneous stranded conductor, maybe all are made by copper. we are using in the house wiring. Where will use solid? Where we will be using solid? For a low rating machines, we will be using solid. Windings of low rating machines. Low rating machines will be using the solid conductor. Okay. And one more application is there for solid. Particularly you see in the dish wire cables. Dish wire cables in our house. It's a coaxial cable with a copper conductor at the middle. It's a solid. Copper conductor at the middle, it's a solid. Okay. So generally these solid conductors will find their applications in the communication systems. Okay. So can be used in the communication systems. Communication lines, you can say. Communication lines. Yeah. So this will be the end of types of conductors what we have discussed till now. And of course, this is the end of the first chapter, basic concepts of power transmission. So let's move to the next chapter, that is line constants calculation. Transmission line constants calculation. That's the next chapter I'm going to take. Okay. Yeah. So this is our next chapter. This transmission line constants calculation. Particularly, we will be concentrating on RLC parameters. RLC parameters. Moreover, I can say positive sequence RLC parameters. Positive sequence RLC parameters calculation we are going to concentrate. Yeah. See, I'll take up first one three-phase transmission line, right? So 3 wires I will show simply. Just look here. So it's a phase A wire, okay, and it's a phase B wire, and I'll say it's a phase C wire. Just listen to the things what I'm saying. A, B, C, 3 wires you have, 3 conductors, and ground you will have something. See, I want to do per phase analysis on this one. Just listen. See, whenever you want to do per phase analysis on this one, we are going to draw per phase network. Means, I'll say simply, I'm going to draw the equivalent circuit of phase A conductor. After drawing equivalent circuit of phase A conductor, right, we will do analysis on that. And the same analysis we will extend for the remaining 2 phases also. That's the what we call easiness. What we are going to get is the per phase analysis of the system. Okay, listen here. So I'll say per phase equivalent circuit here. Per phase equivalent circuit, or you can say phase A equivalent circuit. Okay. See, first of all, while you are constructing this equivalent circuit, I'll say few terms here. Just observe. Definitely, each and every conductor will have some resistance because it is made by some material having some length, okay, some cross section area. Definitely, each and every conductor will have their own resistance. I'll keep that. Resistance of phase A conductor, phase B conductor, phase C conductor, and we are drawing this only for the phase A. So I'm showing only this resistance of the phase A conductor. I have shown. Okay, listen to my words. Don't confuse. Don't confuse. Kindly understand this. Kindly understand this one. See, each wire is carrying their own current. Maybe balanced currents only. Balanced currents, you can say. Okay. So each wire is carrying their own current, so-called balanced currents. See, whenever conductor is carrying some alternating current, maybe alternating current, it will have their own magnetic flux linkages, which we can say self. And it will be causing for some self-induced EMF. Self-induced EMF in the conductor A. Similarly, we have some mutual linkages between conductor A to conductor B, conductor A to conductor C, conductor B to conductor C also. So in that perspective of linkages, self-linkages and mutual linkages, self-linkages and mutual linkages, I used to have some self-inductance of conductor A. We are talking about only A now. We are talking about only conductor A. We have some self-inductance for conductor A, as well as we have some mutual inductance between A and B. We have some mutual inductance between A and C also. A and C. We have some mutual inductance between A and B conductors, and we have some mutual inductance between A and C conductors. Now, we have to keep some inductance in the equivalent circuit. We have to keep some phase A inductance in the equivalent circuit. Which inductance we will take now? Is it self-inductance or mutual inductance or combination? Which inductance we should take now? Is it self-inductance or mutual inductance or combination? Definitely combination. Combination of both we have to consider. So that's why I'll keep some inductance here as LA, phase A inductance or per phase inductance, LA. And this LA, it is a combination of self and mutual inductances. Combination of self and mutual inductances. Mutual inductances. Don't confuse. All these terms will be repeated again and again. Inductances. Self and mutual inductances. Next thing. See, generally, these conductors are operating at their own potentials. Conductors are operating at their own potentials. Maybe conductor A is operating at a potential of B phase at an angle 0 degree. Conductor B operating at a potential B phase at an angle minus 120. Conductor C operating at a potential B phase at an angle plus 120 degree. Balanced voltages I have denoted. All of you understanding? Bundle conductors I will discuss in this chapter. I have mentioned already. Bundle conductors will be dealt in this chapter. Okay. Let me continue. These are the phase voltages. Conductor A, conductor B, conductor C. Generally, for the formation of capacitance, we have certain conditions. Let me tell you. Certain conditions. First condition will be there should exist two conducting bodies. First condition, there should exist two conducting bodies. Second condition, between them, there should be some dielectric material. Between the two conducting bodies, there should be some dielectric material. Next condition, potential gap must be there. Potential gap must be there between them. Okay. Now, one very simple question I am asking you. Can we have any capacitance? Existing between conductor A and ground? Existing between that conductor A and ground? Anybody please tell me? Can we have any capacitance existing between conductor A and ground? Definitely. How in the sense? I'll say in a simple word. A, it's a conductor. Ground is also treated as conducting body. Between these two, we have air gap. And this conductor A is operating at a voltage of V phase with respect to ground only, because ground potential is 0. So definitely there exists some capacitance between that conductor A and ground, right? Something like this, you can say CAG. Between B and ground also we have some capacitance existing. You can call this as CVG. And between conductor C and ground also we have some capacitance existing, CCG. Okay. So, but these are conductor to ground capacitances, which we'll say stray capacitances, are negligibly small. These stray capacitance are negligibly small. Okay, but you see, between A and B, some capacitance will exist. I'll write the name of these things. Stray capacitances which are neglected. Let me continue. Let me continue with this word. A to B, definitely we have some capacitance. B to C, we have something. C to A also we have some capacitance. These capacitances are dominating capacitances generally. These capacitances will be dominating capacitances. Dominating capacitances, right? So it is CAB, CBC, and this was of CCA. These are dominating capacitances. Now, by neglecting those stray capacitances, we are going to consider only these capacitances, CAB, CBC, CCA, and we are going to take up the per phase capacitance, whatever we are going to get, right? Phase A, effective capacitance of the phase A conductor to zero potential. Okay, so that capacitance I am going to show in this figure as capacitance of A to neutral. Better word is capacitance of A to neutral. It's a terminal of neutral, zero potential you can consider. Capacitance of A to neutral, CAN, you can see, CAN. Stray capacitance are neglected. We are considering only these capacitances. If you want, but CAB, CBC, CCA, these are going to be called as interline capacitances. Interline capacitances, which are appreciably high. And this delta, you can see it's a delta, right? A to B, B to C, C to A. It's a delta. If you convert that delta to star, we get the effective capacitance of conductor A to neutral. That we are keeping here. Okay. Yeah. So not only these three elements what we have shown, else I'll say per phase model from this one. Okay, in the next slide I will show. Next slide. Here, per phase. Equivalent circuit of line consisting these elements, what we say. It is a resistance of any one of the phase conductor. Okay, maybe RA you can consider. It is a inductance of any one of the phase conductor. You can consider it as LA. And this is a capacitance per phase value we have. It's a capacitance per phase we have shown. Okay, listen. Just listen to the things. Don't confuse. I will be repeating these things maybe in the separate discussion of the resistor, inductor, capacitor. Don't bother. Even though you are missing some point, don't bother about it. We will be discussing about these things separately in the resistance calculation, inductance calculation, as well as in the capacitance calculation. Okay, listen. See, these are some general talk, what we can say. See, if you want to convert a physical system into its electrical equivalent, we should take up each and every effect what you have in the physical system, that we should keep in an element form in the circuit. In the circuit, we should keep each and every effect as an element. That's the thing what I'm saying. Okay, now Now the thing is, generally if the conductors are carrying some current, definitely there is some heat generation in the conductors, heat production in the conductors. That heat we are going to represent in the form of resistor in the electrical equivalent circuit. Don't write, just listen. I will write these things while I am going for the separate discussions. Just listen. So what that resistor is representing now? Simply it's going to represent the heat generation in the power conductor during the current flow. Generally, whenever conductors are carrying some current, producing some magnetic flux linkages, that magnetic flux linkage represented by this inductor in the electrical equivalent circuit. This inductor, what I kept in the circuit, represents the magnetic flux linkages occurring in the transmission lines. Similarly, we have some electric flux linkages produced by the transmission lines that is going to be represented in the form of capacitance in the electrical equivalent circuit. Simple term, resistance is representing the heat, L represents the magnetic flux linkages, C represents the electric flux linkages. Okay? Yeah. Now, if you go in a practical view of the power transmission line wires, practical view of the wires, see, generally, if you think about this as a transmission tower cross arm, and this tower is getting grounded, and you consider this as a power conductor, and between this tower and power conductor, definitely we have one overhead line insulator. I'm showing that overhead line insulator simply like this. It's a overhead line insulator. So why you are keeping that insulator? In the sense, already we said, in order to withstand the stress experienced from conductor to tower, to experience that electric stress, we are keeping that insulation. That's one reason. Other reason, to avoid the flashover. Yeah, to avoid the flashover. Yeah, to avoid the flashover between the conductor to tower, we are keeping this overhead line insulator. But even though you say we are keeping a high level of insulation or something, definitely, there will be some leakage current. Passing from conductor on the surface of insulator to the tower and then diverted to ground. Something like this, you can say. Okay, like this we have some definite, minor, very less of course, a minor amount of that leakage current will be passing to ground from conductor through the surface of the insulator body. Okay, my question is very simple to you. Is it required to keep this leakage current into circuit or not? Is it required to keep this leakage current into the electrical equivalent circuit or not? Yes, definitely. See, whenever you want to construct a perfect equivalent circuit, definitely this leakage current also has to be kept into the electrical equivalent circuit. We should not neglect. Okay, after some time, I will say this is negligibly small, so that we will remove it and we'll continue with only RLC. I will say that statement later. But for time being, let me keep that leakage current also into the electrical equivalent circuit. Generally, this conductor is operating at a voltage of V phase, and that leakage current I will be writing as that phase voltage V phase by surface leakage resistance of the body. Surface leakage resistance of this body. Okay. So, as a leakage current is a shunt current. We have to keep one shunt element here. Moreover, it is in the nature of resistive. So I will be keeping some resistive shunt element. Something like this. Keeping some resistive shunt element. Yeah. Next, listen to. See, in the way of network analysis, I'm talking very simple network analysis point. Series element will cause for what? In the circuit, series element will cause for voltage drop. Series element will be causing for voltage drop. Shunt element is causing for current drop. Okay, series element causes for voltage drop. Shunt element will be causing for current drop. So what is the voltage drop formula? I into Z. I into Z is a voltage drop formula. Current drop, current drop formula, V by Z. V by Z. Rather than writing that as V by Z, I will write that as V into Y. V into Y. So, in a easiness in the network analysis, series element generally represented in the form of impedance. Series element represented in the form of impedance, whereas shunt element will be represented in the form of admittance. Shunt element will be represented in the form of admittance. All of you getting my point? For easiness in the analysis, in the whole transmission line network analysis further, whole transmission line network analysis further, I used to keep series element in the form of impedance, shunt element in the form of admittance. What is the admittance of resistor? What is the admittance of the resistor? That admittance of resistor is nothing but conductance. Admittance of resistor is known to be conductance. And this is called as generally shunt conductance. Shunt conductance, which is going to represent the leakage current flow. Okay, so I'll say G, that is a shunt conductance. Shunt conductance. G, it represents the leakage current flow. Leakage current flow. Okay? Leakage current flow. So have a break for 10 minutes. After break, we'll be continuing with this one. Okay? 10 minutes break. After break, we'll be continuing with this. So I have resumed audio video on screen. So kindly confirm, is it audible? Yeah. So let's see some other what we call practical effects what we have in the system. Some other practical effects what we have in the system, how we are going to keep that into the circuit. Okay. So particularly I'll say about corona. Corona in the transmission line wires. In what element we have to keep that corona in the transmission line wires? That's the thing I will say in a brief way. See, basically, corona, it's an ionization on the conductor surface, I said at the beginning class. Corona is an ionization on the conductor surface. Ionization means it's a glow, it's a light, it's a light. So light is obviously, it's an energy. Light is obviously an energy. It's a loss now because we are not using it for any purpose, right? So corona is an energy loss, you can say. Corona is an energy loss. All of you getting my point? Please tell me. All of you getting my point? What I said now? Corona is an energy loss. Why? In the sense, we have an ionization on the conductor surface. It's a light. Light is a form of energy which we are not using for any purpose. So it's a loss. It's a loss. Okay. So corona loss, in what form we have to represent in the electrical equivalent circuit? See, in this circuit, I have two elements which are what we call representing the power loss. Two elements which are representing the power loss. One is a resistor series. Next one is a conductance shunt. Among these two, in which element we should keep that corona? In which element we should keep that corona? Tell me please. Is it a series element or shunt element? Which element we should keep? I will ask you one simple question. Corona is caused by current or voltage? Corona is caused by current or voltage? Tell me this answer first. Corona caused by current or voltage? Voltage. So as it is caused by voltage, we should keep that as a shunt element. We should keep that as a shunt element. Means in this G itself, I should keep the corona also. So I can say in the next slide, in this point itself, shunt conductance, what we kept here, that's also representing corona loss in the transmission lines. Corona loss in the transmission line. Okay, next. Next. See, generally, in the air gap between the conductors, there exists some dielectric loss. In the air gap between the conductors, there exists some dielectric loss. In which element we should keep that dielectric loss? That is also in the parameter G. Why it is so means dielectric loss is again depending upon the voltage. So as it is depending on the voltage, it is better to keep that in the shunt element form. So I can say shunt conductance G also represents dielectric loss. Dielectric loss occurring in the air gap between the conductors. Air gap between conductors. Air gap between the conductors. Okay, but one more thing here. The shunt conductance G, what we are discussing now, it is highly depending on the atmospheric conditions. The shunt conductance G highly depending on the atmospheric conditions. Because at leakage current, what is going on the surface of insulator definitely depends upon the conditions like whether it is a hot season or cold season, winter season, rainy season. Definitely it will be depending. Corona loss also depends on the same. Dielectric loss also depends on the atmospheric conditions. So this parameter G, I'll say simply, it is highly dependent on atmospheric conditions. Atmospheric conditions. Expecting this number is very difficult. Calculating the value of G is very difficult. Not only that, it is a negligibly small value. It's a negligibly small value, so that most of the times in our analysis, we are going to neglect this parameter G. We will be continuing with only RLC parameters calculation. Okay, so G is very low value, practically speaking. G is very low value. That implies it can be neglected. It can be neglected in most of the studies. Most of the studies. So that's why we neglect the G, and our main concentration will be only on the calculation of RLC parameters of the transmission line. RLC parameters of the transmission line we are going to concentrate mainly. Okay, so let's take up the first heading, that is calculation of resistance of the transmission line system. Okay, so till now all of you clear in this chapter? Yeah, temperature sensitive, pressure sensitive, all things. G, it's an element which is depending on the temperature, pressure, wet conditions, all these things. Yeah, fine. So I'm taking up in the next slide. I'll see, Ramakrishna, you have attended that fault analysis, right? Fault analysis. So obviously we are giving positive sequence voltages and currents. Right? Positive sequence voltage and currents. Based on that, we are calculating the parameters. Rashmi, what you have not clear? Can you please tell me? What point you have not clear? Can you please elaborate? Yeah. Yeah, fine. Sir, why voltage related to shunt? So why voltage related to shunt means based on that voltage only that shunt element is going to draw current, right? Based on the applied voltage only, that shunt element is going to show its effect. Current drawn or current delivery or power or whatever it is. Okay. Yeah. So let's move ahead to the calculation of resistance of transmission line as a next heading. Of course, it's the first element in our study. Calculation of resistance. Calculation of resistance. Yeah. So let's say, first of all, what is the formula for this resistance? First of all, what's the formula for resistance? R equals to, we know it is rho L by A. It's a general formula what we discussed in the previous class also. I'll write simply R is equals to rho L by A. One thing. Stop writing and just listen. Stop writing, just listen. Yeah, listen. See, whatever the A I am showing, in this vertical equation, this A is a total cross-section area of the conductor I am saying. Whole, total. It's a total cross-section area of the conductor or physical cross-section area. Physical cross-section area. Then what is this resistance name you can give? Anybody tell me please? What we name this resistance? Yesterday itself we have discussed about it. This is going to be called as DC resistance of the conductor. Right? If you are considering the total cross-section area in the resistance formula, means you are saying that in the total cross-section area the current is passing. Means obviously this resistance is going to be called as DC resistance of the conductor. DC resistance of the conductor. Sometimes this can also be called as ohmic resistance of the conductor. Ohmic resistance of the conductor, or you can say DC resistance of the conductor. But is it the resistance what we need to take into circuit? Is it the resistance what we need to take into circuit? Yes or no? No, we should not take this DC resistance into circuit. We should go for only AC resistance into the circuit. What is the formula for AC resistance? What will be the formula for the AC resistance? RAC equal to rho L by A dash. RAC, that will be equals to rho L by A dash. Okay. Dinesh Kumar, you please ask for doubt in doubt session. I will explain about it. Capacitance, it's a simple thing only. Look here. RAC equals to rho L by A dash. This A dash is the area through which the AC current is passing. Okay. AC current flow area. AC current flow area. AC current flow area. I will ask one very simple question to you. Very simple question. Is it possible to measure this A dash value? Is it possible to measure this A dash value? Means area through which current is passing. Is it possible to measure? Exactly. No, it is not possible to measure that. But you can guess that value by using skin depth. You can guess that value by using skin depth, but that is again an approximate one. Strictly speaking, it is not possible to know exactly how much is the value of A dash, but we can expect it. We can approximate it. Based on that, whatever the resistance you calculate, that is an approximate resistance only. It's not an exact resistance value. Okay, so I will write that word here. A dash can't be calculated or can't be measured directly from conductor. Can't be measured from conductor. Measured from conductor. But it can be expected or estimated also, you can say. It can be expected. So that in that view, I can say whatever the RAC we are calculating from this formula rho L by A dash, it is not an exact resistance calculation. So it's not exact calculation of resistance. Not exact calculation of resistance. Okay, what is the exact calculation of resistance? We'll think about it. Before moving to that exact resistance calculation, I'll try to tell you what is the significance of this resistance placement in the circuit. Why we are keeping that resistor in the electrical equivalent circuit? In that perspective, we are going to discuss. Okay, so I'll show in the next slide. Significance of resistance placement in the circuit. Why we are keeping that resistance in the transmission line equivalent circuit? What is the first significance I said? Already? It will be representing the heat generation in the conductor, right? So I can say first significance is R represents the heat generation in the conductor. Heat generation in the conductor. Okay, this one thing. Second significance I am saying, just listen to this one. Second significance. Heat generation, or you can say power loss also. Heat loss also you can say. Okay, listen, second one. See, actually, whenever we have some current flow in the conductor, there is some opposition shown for the current flow. There is some opposition shown for the current flow by means of this resistivity. By means of the resistivity, there is some opposition shown for the current flow. How we will model that opposition for current flow in the circuit? Opposition for current flow in the circuit is going to be modeled as voltage drop. Opposition for current flow means it is going to be known as voltage drop. Okay, that voltage drop we are going to keep in the form of the resistance in the electrical equivalent circuit. Okay, so I'll write R represents the opposition for current flow. In bracket I can say voltage drop due to resistivity property. due to resistivity property. Okay. So R represents the opposition for the current flow due to resistivity property. Yeah. Now let's say, for example, so we are taking one three-phase transmission line to the lab, maybe 1 kilometer or 2 kilometer length of line we are taking to the lab like this. It's a three-phase line. And one side you can have input, other side you can have output. One side we have input, other side we have output. Just listen to my words, what I'm saying. We are having some output power like this. We are having some input power, something like this. It's a three-phase line. So after knowing how much amount of power you are getting as an output, after knowing how much amount of power you are giving as an input, definitely the difference what we have between them, input minus output, what we'll say that definitely it's a power loss in the transmission line. Yes or no? So I can say power loss in the transmission line. Power loss in the transmission line is nothing but this input minus output. Input minus output. And you say it's a three-phase power loss right now. Three-phase power loss means what I am saying here is you are capable to calculate the power loss by a practical experiment. You are capable to calculate the power loss by a practical experiment that we are saying as simply input minus output in the practical experiment. Okay, listen. After knowing this number, what is the power loss formula from circuit analysis? After knowing this number, what is the formula for the power loss from circuit analysis? It will be 3 into I square R. It will be simply 3 into I square R. And you should match the 3 into I square R to this. By that way, we can get the resistance of the transmission line. Okay, so I can say from this, as we know, 3 into I square R is nothing but three-phase power loss. So I can say resistance is nothing but is three-phase power loss value by 3 times of current square. 3 times of current square. So could you please tell me whether the skin effect is perfectly involved in this resistance? Now, why you have neglected the previous formula? Why you have said this is not exact formula? Reason is skin effect may not be taken care properly. Skin effect may not be taken care properly in the previous formula. That's why we are avoiding it. We are saying this is not exact one to know the resistance value. But in this formula, are you sure that skin effect is taken care properly? Are you sure that the skin effect was taken care properly? Yes. Yes or no? See, actually, we don't know what is happening, right? We don't know what is happening. Simply, we are giving some input power, taking some output power, and difference we are saying as loss. In that loss, what we calculated practically, skin effect was taken care perfectly. So, this resistance we are going to call as effective AC resistance of the transmission line. So, this we are naming as effective AC resistance of transmission line. Effective AC resistance of transmission. Exact, or you can say it's a effective AC resistance of the transmission line. So I think all of you getting this clear? We are calculating the resistance maybe per kilometer now, per kilometer. Lumping in the sense that depends upon the number of kilometers. It may be, you can feel it's a per kilometer resistance, Vishnu. Ankur. Okay, done. Next thing. Let's take up these discussions quickly. First, I'll take a DC two-wire system resistance calculation. Next, DC one-wire system resistance calculation. After that, we extend that to single-phase two-wire. Finally, three-phase system. That's it. Quickly, we'll do this. DC two-wire system. I am taking up first. DC two-wire system. Two-wire system. So we have two conductors, one as a forward and the other as a return. So I'll show here. It's a forward conductor and it's a return conductor. Yeah, forward and return. You name it's a conductor A and it's a conductor B. And this side, I'm keeping one voltage source, DC voltage source, and this side I'm connecting one load. It's R load. Okay, now we have some current flow. Just check this. We have some current in this conductor A going in this way and circulating back in this line. Circulating back. Yeah, listen. Conductor A might be having some resistance of Ra. Conductor B is having a resistance of Rb. Conductor A resistance we are calling as Ra. Conductor B resistance is Rb. The effective AC resistance is nothing but resistance which including the skin effect. Already we discussed about relation between AC and DC yesterday. Yesterday we discussed about relation between AC and DC resistances. Okay, let me continue with this. See, we have some input voltage here, source voltage, you can say as Vs. And it's a load voltage, you can call it as VL. Source voltage and load voltage. See, in this particular DC two-wire system, we are going to say about what is a loop resistance of the system, or what is circuit resistance, what is system resistance. These are the terms which we are going to concentrate. See, that loop resistance or circuit resistance or system resistance is nothing but the resistance value which is causing for total voltage drop. Resistance value which is causing for the total voltage drop, that we are going to name it as loop resistance or circuit resistance here. To get the total voltage drop, you apply KVL to this loop. So that we can get VL minus VS minus VL. That itself is a total voltage drop. Input voltage minus output voltage. Okay. So let me write. KVL for loop. So what it will give is VS source voltage minus I into RA voltage drop. Next VL, it's also voltage drop only, minus I into RB, that is equal to 0. Now the total voltage drop is VS minus VL. This you can get as I into RA plus RB. If you take that I into RA to the other side, I into RB to the other side, you get I into RA plus RB. And whatever that RA plus RB we have now, that we are going to name it as loop resistance or circuit resistance of the system. Okay, so I can say loop resistance, loop or circuit or system, any name you can say, system resistance. You can name it as R total is equal to RA plus RB. R total is equal to RA plus RB. Loop resistance, or you can say circuit resistance, or you can say system resistance. It will be RA plus RB. Forward plus return. So can I use the same formula for single phase two-wire system also? Can I use the same formula for the single phase two-wire also? Yes or no? See, even in case of single phase two-wire, we have a forward conductor and a return conductor. Both are connected in series. Sum of the two resistances is nothing but loop resistance in case of the single phase two-wire. Yes? Okay. So I can say here R total equals to RA plus RB. This can be used even for single phase two-wire also. Used for single phase two-wire system also. Okay, done. Next thing. So I'll say about DC one wire here. So A is a forward conductor here. A is a forward conductor and B is a backward or return conductor. That's the meaning. Return. Let's move. So I can say DC one wire system. DC one wire system. One wire system. So we have only one conductor now. We have only one conductor which will be acting as forward. And who is going to act as the return conductor? Ground. Earth is going to act as a return conductor now. So I can say first, this is a forward conductor I'm showing, A, conductor A, and ground is acting as a return, maybe something like this. Ground acting as return. Ground return. Okay, so this side I will keep one voltage source, other side we are going to keep a load. Voltage source like this, and other side I'm keeping some load. Yeah. So now you see this conductor A, so-called forward, is having some resistance of Ra. Ground, or you can say earth, might have a resistance of Rf. Or earth. Yeah, current will flow through ground. Current will flow through ground. Yeah. Next. So in this case also, if you want to consider the total resistance or loop resistance, you should say simply forward plus return. So called Ra plus Ra. So here also you can say total resistance, loop resistance is nothing but Ra plus Ra. Ra plus Ra. But how is that earth resistance value to be expected? How is the earth resistance value to be expected? It's negligibly small, very, very low number. Very, very low number we can see, right? Else as an expectation. As an expectation, let's go with the formula earth resistance equals to rho L by A. Earth resistance is equals to rho L by A. I will try to explain each and every term in that formula. By that way, we'll come to know that earth resistance may come very close to 0. Yeah, let's move. Earth resistance we are talking now. Earth resistance. We are saying it is rho L by A. Rho L by A. First you tell me, what do you mean by rho here? What do you mean by rho? Resistivity? That's okay. We should call it as soil resistivity. Rho is going to be called as soil resistivity. Soil resistivity. Okay, how is this number generally? How is that number soil resistivity? It will be in the order of 100 ohm meters. So some places might have very low, some places might have very high, but on an average, soil resistivity will be 100 ohm meters. 100 ohm meters. Is it a low value or high value? Is it a low value or high value? It's very, very high value. It's very, very high value. Resistivity of the soil is very, very high. Because, you know, for conductor, so-called for aluminum conductor, you talk, aluminum conductor, resistivity of aluminum conductor will be around 2.8 into 10 power minus 8 ohm meters. Aluminum resistivity is around 2.8 into 10 power minus 8, whereas the soil resistivity is around 100. So soil resistivity is very, very large number as compared to the resistivity of aluminum or our power conductors. That's one thing we have to identify. Okay, next term. Kindly listen. L. What's it? Length of current flow. L is a length of current flow. Na? What is that length of current flow? That is the length starting from this grounding point of load to the grounding point of source. Means the current might be passing in this direction, you can say, and how much amount of length this current is passing means that will be equal to the length of the conductor A. Length of current flow is nothing but length of the conductor A itself, you can see. Okay, next. Maybe it's 20 kilometers or 30 kilometers. That number we should consider. Next, what is A? A is the area of cross section. A is the area of cross section measured perpendicular to the direction of the current. A is the area of cross section measured perpendicular to the direction of the current. See, for example, current is flowing on the surface of ground, something like this. Okay, so area we should measure perpendicular to this, means we should measure that area in the downward direction. Should measure the area in the downward direction. So if you look in this manner, how that earth looks to be for you, it's a circle. Earth looks to be a circle, and the circular cross section we should keep in this calculations. Okay, so what is that circular cross section? Pi r square. Pi r square is a area of cross section to be expected. And what is that earth radius now? Earth radius r is equals to around 6,800 kilometers. 6,800 kilometers is a earth radius. As this radius is very large, very large, expecting that area is very high, and definitely earth resistance is very low, and we can approximate that number very close to 0 in most of the calculations. Okay, so I can say earth resistance will be approximately equals to 0. Earth resistance is approximately equals to 0. Ah, 6,800 or 6,400. What is the correct number of radius of Earth? Tell me. Somebody is saying 6,400. By mistake, I might have written. It may be 6,400 only. 6,800 or 400. Just try to cross check that number. Earth radius. Of course, it is very large. You can say 6,800. Okay, check that number. Check that number, and of course, it's in the order of 6,000. In the order of 6,000 kilometers. Okay, let me continue. So earth resistance is very low value we are saying. That's why we can say this total resistance might be equal to conductor A resistance itself. So I can say total resistance R total is equal to approximately equals to conductor A resistance itself. Yeah. 6,400. Approximately. Yes, next. So can we use the same formula for single phase, single wire also? Yes, we can use the same formula even for single phase, single wire system also. Can be used for single phase, single wire also. Single phase, single wire also. Okay. So next, let's think about the three-phase system quickly. Three-phase system. Resistance. Comment on the resistance of three-phase system. So I'll say three-phase system here. So we have three conductors here. Phase A, phase B, phase C. Having their own resistances like RA, RB, RC. RA, RB, RC resistances. And we have to call only per phase resistance here. Per phase resistance is nothing but resistance of any one of the phase conductor. Any one phase conductor. Maybe you can say it is simply RE also. Resistance of any one of the phase conductor, you can call it as RE. Okay, done. Next thing. See, till now we have discussed about number of systems. I want to discuss about the practicality of each and every one. Practicality. Three-phase system is very practical to us outside. Yes or no? Most of the times we are dealing with three-phase AC transmission system. So three-phase system is very practical in the overhead lines. Next one. Let's move back and what about DC two-wire? Is it practical? DC two-wire. DC two-wire system. Is it practical or not? Yes. In the HVDC, it is going to be known as bipolar HVDC line. Bipolar HVDC line, we can say. DC two-wire system The best example for bipolar HVDC line. Bipolar HVDC line. Next one. DC one wire. DC one wire. Is it practical? DC one wire. Yes, it's also practical, and it's going to be known as sometimes monopolar HVDC line. Monopolar HVDC line. We have these lines also in India. Okay, we have bipolar HVDC line, practically DC two wire. Monopolar HVDC line is also practical DC one wire. What about single phase two wire? What about single phase two wire? Is it practical? Single phase two wire. Is it practical? Yes or no? Tell me please. Single phase two wire. Is it practical or not? Yeah. Yes. Particularly in the secondary distribution system. Secondary distribution system. We'll be using single phase two wire system. One as a phase wire, return path as a neutral wire. So it is practical in secondary distribution system. Secondary distribution system. Secondary distribution system. It is practical. Okay, next thing. What about single phase, single wire? Single phase, single wire. Is it practical? Single phase, single wire. Is it practical or not? Tell me. Yeah. So it is practical in electric traction. Electric traction. We used to have only forward conductor on the top. Return conductor is going to act as a railway track. Okay. So it is practical in traction. Electric traction. Electric traction. So all the systems what we have discussed till now are practical things only at various places, and they have their own applications. Okay. Yeah. So this is sufficient to know about the resistance calculation. We don't get generally a question on resistance calculation. We used to get questions in inductance and the capacitance calculations most of the times. Let's put concentration on those calculations mainly. So I am taking up in the next slide, that is calculation of inductance of transmission lines. Okay. So next reading, calculation of inductance of transmission lines. Transmission line. Okay. Calculation of inductance of transmission. This is one of the very important topic for the examination. One of the very important topic for the examination. Electric traction, 25 kV. Why can't it possible? Big voltage. Yeah. Let's think about this. Basic thing I am going to discuss first. What is a basic definition for the inductance? Basic definition for the inductance I am going to write as inductance is defined as a ratio between magnetic flux linkages and current. Ratio between magnetic flux linkages by current. Magnetic flux linkages by current. This is a basic definition to say about inductance. Else, in the way of notation, if you want to write notations, L is equals to psi by I, we can say. L is equals to psi by I. But strictly speaking, we should not write this as psi by I. Should not write this as psi by I. What we should write is L is equals to rate of change in the flux linkage with respect to current. Rate of change in the flux linkage with respect to current. So this is always a perfect formula to be used. This is the exact formula to be used in the calculation of the inductance. And when we will use that psi by I? When we will use that psi by I? Maybe in the cases of linear. So this is used only for linear cases. Only for linear cases. right? Whereas whether the inductor is a linear inductor or non-linear inductor, in all other cases, we can go for L is equals to d psi by di, which is valid in all cases, as we said just now. Okay? Yeah. Next. Before moving ahead, let me tell you whether the transmission line inductance is a linear one or non-linear one. That we have to comment. Whether the transmission line inductance is linear or non-linear. That we have to comment. To do that comment, I will discuss little about the BH curves. Okay? Yeah. Just listen here. Very simple thing only. For example, one minute, please. Yeah. For example, so I will show some graph here. Just look. So it's a BH curve, as I said just now. Y-axis, we have B, magnetic flux density. H is a magnetic field intensity. But rather than taking that B and H, you can take here psi, and here you can take I also. Yes or no? BH curve and psi versus I curve, both will be same. Tell me now, how is this BH curve? Is it a linear variation or non-linear variation? How is it BH variation? Is it a linear or non-linear? Anybody tell me, please? Who will decide it? Who will decide whether we are going to get the BH as linear or non-linear? That depends on, listen my words. That depends on material over which we get the magnetic linkages. In what material you are getting the magnetic flux linkage will decide whether this BH curve is a linear or non-linear. For example, if you are getting, listen please, if you are getting magnetic flux linkages in a magnetic material, then definitely there will be a saturation above certain current. There will be a saturation, so that you don't get a linear shape all the time. You will get some non-linear shape beyond certain value of current. Okay, so you might be getting that BH curve something like this. If magnetic flux linkages psi occurs in magnetic materials. Psi occurs in magnetic material. Okay. For example, if the flux linkages are occurring in non-magnetic materials, you don't expect any saturation. You will get as a straight line. You will get that as a straight line symbol. Okay. So let me show. This is a current axis, and this is a psi flux linkages axis or flux axis, you can say. Psi I. And if the psi occurs in non-magnetic material, you'll get this simply as a straight line. Maybe like this, you can say. Yeah. Tell me please. See, whatever the slope of the curve we have here now, psi versus psi. I'm talking about psi versus psi. Whatever the slope of the curve we have here, can I say that as an inductance? Inductance value. Nobody is responding. All of you getting this? Tell me please. All of you clear till now? Very basic concept. I am discussing here. So whatever the slope we have here, that is going to be called as inductance. Now you tell me whether this inductance value is constant or changing with respect to current. Changing. So in this case, the inductor is going to be called as non-linear inductor. Okay. So in this case, we can say inductor is non-linear. Inductor is non-linear in this case. Whereas here, the slope of this line remains constant for all the value of current. And in this case, you can say the inductor as a linear inductor. Inductor, we are going to name this as a linear inductor. Linear inductor. So I think all of you getting this? Yeah, very simple, Sunil. Nothing. Very, very simple. Just listen. Just listen. If the magnetic flux linkages are occurring in a magnetic material, there will be a saturation. Because of saturation, psi versus I will be a non-linear shape. Okay. Because of that non-linear shape, slope is changing at each and every value of current. So that inductance value is the slope, d psi by dA. As the inductance value is varying, with respect to current. I will call this as a non-linear inductor. That's it. And if the magnetic flux linkage occurs in non-magnetic materials, we don't have any change in the slope. You will get a straight line. And inductor, we are going to name it as linear inductor. I think all of you getting my words. Is it clear now? Non-magnetic material, best example is air. Surya, Sunil, have you understood this now? Yeah, both are practical. Linear is practical as well as non-linear is also practical. But my aim right now to decide whether our transmission line inductance is linear or non-linear. That discrimination we want to make. For example, simple. This is a transmission line conductor. It's a transmission line conductor. You take it as an aluminum conductor now. Aluminum, is it magnetic or non-magnetic? Aluminum material, is it magnetic or non-magnetic? It's a non-magnetic material. Aluminum material is a non-magnetic material. Okay, next. See, actually, if this conductor is carrying some current, listen please. If this conductor is carrying some current, we have some flux linkages occurring inside to the conductor, which you can say as psi internal. We have some magnetic flux linkages occurring inside the conductor, which we can say as psi internal. And we have some magnetic flux linkages occurring outside to the conductor also, which we can say as psi external. So we have some internal magnetic flux linkage occurring inside the conductor, external linkages occurring outside to the conductor. Outside to the conductor means it is air. Outside to the conductor means it is air. Now the thing is, internal linkages are occurring in aluminum, non-magnetic. External linkages are occurring in air, also non-magnetic. Air is also non-magnetic only. Now can I say both internal and external linkages occurring in non-magnetic material, then definitely you don't have any saturation. If you don't have saturation, inductor of the transmission line is going to be called as linear inductor. All of you understood this point or not? It's a very important one, particularly for interviews. So some people will ask you simply whether the transmission line inductor is linear or non-linear, and you have to explain all these things to them. Okay. So internal linkages are occurring in psi internal and psi external, both occurs in non-magnetic materials. Therefore, transmission line inductance is constant with respect to current. That implies linear inductor. Yeah. Please kindly go through it. Both are equal permeability. Aluminum will have a relative permeability of 1. Air is also having a relative permeability of 1. Okay. Very simple. I have given the basic already here. In this slide, I have given the basic. I think all of you have understood this slide. Okay. After that, what we have to know is whether our transmission line inductance is linear or non-linear. In which category it will fall, that we have to know. To know that, we have to know in what material we are getting the flux linkage. Is it in magnetic or non-magnetic? Okay. So coming back to line, transmission line wire, we have aluminum conductor, which is a non-magnetic. We have some internal linkages occurring in the aluminum material. So psi internal, it will be a linear variation. And external linkage occurring in air gap. Air is also non-magnetic material. So obviously both internal and external linkages are occurring in non-magnetic materials. You will have a linear variation. Psi versus psi will be linear variation. So your inductor will be obviously linear inductor. That's it. Okay. If you have ACSR conductor, we have a little non-linearity. If you have a ACSR conductor, we have a little non-linearity, but that can be neglected. By neglecting that little non-linearity, we are following only this one. Okay. Yeah. Next. Let's continue with this thing. What is the significance of the inductance placement in the circuit? Why we have to keep that inductance in the electrical equivalent circuit? Significance of L in the electrical equivalent circuit. See, one thing already we said, it is going to represent the magnetic flux linkages occurring in the conductor during the current flow. L represents the magnetic flux linkages. Magnetic flux linkages occurring in the conductor. This is one thing. And second one, it will be representing the amount of reactive power. Look here. It will be representing the amount of reactive power absorbed by transmission line under steady state. Okay, I'll come to that reactive power. Maybe at the end of this inductance calculation, I will discuss about that reactive power also. So L represents the amount of reactive power absorbed by transmission line under steady state. Okay, so next, third one. Just look here, third one. Say I will show one transmission line wire here, something like this. It's a transmission line wire. And we have this side AC voltage source. And this side I am showing some load. We have an AC voltage source on one side, and the other side we have a load. Yeah. Good. Just look here. So it is carrying some alternating current. Conductor is carrying some alternating current to the load. See, whenever conductor is carrying some alternating current, because of this, definitely it will be producing some alternating magnetic flux linkage. Alternating magnetic flux and flux linkage, you can say. So we have some magnetic flux linkages created by this alternating current. Magnetic flux linkages created by this alternating current flow, something like this. So I can say it is psi AC, alternating magnetic flux linkages created. Now, what is the rate of change of these magnetic flux linkages? What will be the rate of change of these magnetic flux linkages? That is EMF. d psi by dt, that is EMF. So I'll say E is equals to d psi by dt. That's the EMF. In which direction this EMF is acting? In which direction this EMF is acting? Definitely opposite to the cause. Opposite to the cause in the sense, you can say, it will be acting in opposite direction to the current flow. This EMF is acting in opposite direction to the current flow. Means obviously I can say this EMF is showing some opposition for the current flow. This EMF is showing some opposition for the current flow. What do you mean by opposition for the current flow? Voltage drop. Opposition for current flow is nothing but voltage drop. So I can say, to represent this voltage drop, we are keeping inductance in the equivalent circuit. So L represents the voltage drop due to rate of change in the magnetic flux linkages. Due to d psi by dt, whatever the voltage drop we have, that we are going to keep in the form of resistance. Sorry, that inductance. Okay, this is about the significance of inductance calculation. So we'll stop at this point. Tomorrow we'll continue with single phase two wire system inductance calculation, then single phase single wire system inductance calculation, and three phase system. While we are moving into three phase system, I will introduce the terms like GMR and GMD and all. Okay, and then we will discuss about the bundle conductors. So this is a way how we are going to proceed further. So if you have any doubts, you can ask me. I will make all the hands low. Please kindly raise your hands if you have any doubts. Sweta, do you have any doubts, Sweta?
Sir. Yes, sir. Can you hear me, sir?
Tell me.
Yes, sir. My doubt is regarding ACSR conductors.
Okay.
Sir, in skin effect, we are having that the current is concentrated on the surface only. And for removing that, we are using the stranded conductors. Whereas in the stranded conductors, we have again made the same kind of arrangement that the current is concentrated only on the surface conductors.
But you see, your point is that the skin effect is not reduced. Is it your point?
Yes, sir. I am seeing no difference. Like very.
See, actually, on each and every circle we have skin effect, right? On each and every strand we have skin effect.
Okay, sir. Means it is reduced to some extent, not totally.
Not that's what I also said. It may not decrease completely, right? For example, you see, if it's a conductor.
Yes, sir.
Right? On each strand, we have the skin effect separately. For example, like this, you have. See, on this strand, you have a depth of current, something like this. Okay? On this strand, also, you have a depth of current. Like that, on each and every strand, you have a depth of current, right?
Yes, sir.
So, in that view, if you compare the solid conductor with this one, definitely, the area through which current is passing is going to be increased.
Okay, sir.
Understood the thing, what I said?
Yes, sir.
Clear?
Sir.
Yes, do one thing. Take one solid conductor, show the current flowing area in the red color. Take the AAC conductor, show the current flowing area like this with the red color.
Yes, sir.
In which conductor the red color portion is more? Obviously, AAC, right? This stranded.
Yes, sir.
Okay. So in that perspective, definitely skin effect will be reduced, but it won't come to zero, what I say.
Okay, sir.
Like this, you can say. And for example, if you have the same sort of solid conductor with the same skin depth, of course, because same material, na? So if it's a solid conductor, you will have the current flow only this portion, this blue color portion. If it's of solid conductor of same size, getting me?
Yes, sir.
Then
I got
obviously this AAC conductor is carrying current in more area comparing to solid, right?
Yes, sir.
Tell me, any more
Sir.
doubt you have? Tell me.
Yes, sir. Sir, in the last part only where you have written that L represents the amount of reactive power. I don't know what does
Reactive
that
power we'll
mean.
discuss. Actually, we have two reactive elements in our system. One is of inductor, other one is of capacitor.
Yes, sir.
Okay, one element we will say it is absorbing reactive power. Other element we will say it is delivering reactive power.
Okay, sir. Sir, what
So,
is the meaning of reactive power?
Please wait for some time. We'll come to know exactly. Huh?
Okay, sir.
Okay, I can't say it now. It will come in a regular class itself. What is that reactive power?
Okay, thank you, sir.
Okay. Salman Khan.
So good morning, sir.
Tell me, Salman Khan.
Yes, sir. I have doubt that if we reduce the size of the strand to the extent of skin depth, sir.
Then obviously you don't have any skin depth.
So why can't we do it practically, sir? Means
Cost
only.
Cost.
Oh, okay, sir. Okay. And another doubt.
See,
Sir,
definitely, without changing size of stranded conductor, if you go for large number of strands,
yes, sir.
skin effect will definitely decrease.
Right.
That's why
Right.
you see in your house wire, you can find a strand of very, very thin size.
Yeah, right, sir. But
to make your voltage drops very low.
Yeah, right, sir.
Okay.
Why don't we insulate those strands separately, sir?
Actually, very low level of insulation coating will be there on the strands. Okay. It's not visible.
That's the reason.
Yeah.
Another doubt, sir. Yesterday's doubt, sir.
Tell me.
That grid voltage, how the current flows from the generators to the grid. If
See,
same
220 kV is a rated voltage of the system.
Okay.
That does not mean that both buses are operating at 220 kV, right?
I thought that 220 kV as bus voltage and
no. 220 kV is a rated voltage. Operating voltages might be different.
Okay, so that's how current flows only.
There will be an angular difference, voltage magnitude difference between the buses during operation. Because of that, only current will flow.
Right, sir.
For example, I'll tell you, Salman Khan, I have one 2-bus system like this. It's a 220 kV rated system, I'll say.
Okay, sir.
Rated system. You tell me what is your sending end voltage and what is your receiving end voltage?
220 kV. Sending a voltage.
I don't know.
Yeah, exactly.
You are saying it's a rated voltage. You are not saying about operating voltage now.
Right.
Clear?
Clear, sir.
Yeah.
Thank you, sir.
Yeah. Kumar.
Sir, good morning.
Kumar, tell me.
Sir, in per phase equivalent representation,
okay.
Mutual capacitance is there, line to line capacitance.
Yeah.
In per phase you represented, sir.
That delta we convert into star, I said, no. Whatever the delta you have, A to B, B to C, again C to A. This delta you have, right?
Yeah.
The delta we convert to star.
Star.
Then you get A to neutral capacitance.
Okay.
That A to neutral capacitance we are keeping in the circuit.
What about ground phase?
That we are neglecting, which is very low, I said, right? Because height of the conductor with respect to ground is very high.
Okay. Sir, 0 volts means only in balanced condition, right? Otherwise,
we are constructing the circuit only in the balanced operation.
Only in balanced operation.
Else you consider it as positive sequence operation only.
Yeah. Okay. Per phase is only for balanced.
Per phase, yes.
Okay, sir. Thank you, sir.
Okay.
Sir, I have another doubt.
Tell me.
In rectangle shape at edges, E is more, so corona effect is more. You said.
More, yes.
So, but in rectangle shape, the most distance from the center to the edges is more.
No, not because of that reason. Actually, you have to think about that electric field intensity as rate of change in the voltage with respect to distance.
Yes, sir.
dV by dx.
Yeah.
So the rate of change in the voltage in which direction it is very high. In that direction, we get the more field intensity.
Okay.
Okay, not distance from center to that point. Change in the voltage is the main concentration there.
Okay, sir.
Okay.
Okay, sir.
Yeah.
Thank you, sir.
Shraddha Chavan.
Hello, sir.
Tell me, Shraddha.
No, sir. Why do we take line current equal to phase current in case of transmission lines?
You see, we have three wires like this, phase A, phase B, phase C.
Yeah.
And you say line to line voltage, we have something. Okay.
Yeah. Yes.
And each conductor is operating at a voltage of V phase.
Yes,
Line to
sir.
line voltage equals to √3 times of V phase in magnitude.
Okay.
And whatever the current flowing in the line, that current itself can be called as phase current now.
Yes, sir.
That's it.
Okay, sir. And sir, one more doubt. Can we say skin effect as eddy current loss in the transmission line?
Can't say exactly eddy current loss.
Equivalent to eddy current loss.
No. Actually, you are attempting to relate this with your transformer. Is it?
Yes, sir.
See, in transformer, in the core, we are getting that eddy current circulation unnecessarily,
Yes, sir.
causing a loss called as eddy current loss.
Yes.
But in our conductor, current flow is necessary, right?
Yes, sir.
Getting the difference.
Okay. So we don't
We should not call it as eddy current loss.
Okay, sir.
Because
sir,
of eddy currents, current distribution is becoming non-uniform.
okay.
That is leading to low cross-section area current flow,
Okay, sir.
leading to more resistance and more power loss.
Okay, sir.
That you say, but you can't say this as eddy current loss.
Yes, sir. And sir, do we consider the loss due to skin effect in the power loss?
Yeah, that's what I said. I don't know what's happening in transmission line at all here in this practical exercise. I don't know what's happening in the line. We are giving just input power and taking out power.
Yeah.
Whatever the difference we have there, that is a loss due to what? Resistivity, skin effect, all the things.
Okay, sir. Yeah.
That we have represented in the form of series element by equating that loss value to the equation from circuit analysis. Who is saying this equation for us? Circuit analysis.
Yes, sir.
This is who is saying this power loss? Practical experiment.
Okay, sir.
By relating these two, we attempt to get the resistance to be kept in the circuit.
Yes, sir. Understood. Thank you, sir.
Okay. Yashwant.
Sir. Just now my doubt got clarified in the effective AC resistance, sir.
Okay.
But
Any other doubt here?
Yes, sir. But DC one-wire system, how will the sir? Suppose the earth is the return path. Conservation of charge must be happening in the circuit now, sir. Will that happen in DC one-wire system?
Definitely.
How, sir? I mean, ground can't supply the charge back to the source, no, sir.
No, ground we are using as a simple conductor.
Okay.
Ground we are using as a conductor. If you assume that resistance is 0, then obviously both load grounding point and source grounding points are joined, right?
Yes, sir.
That's it.
So from the load ground point to source ground point, I mean, there will be charge flow.
There will be charge flow.
Oh, okay, sir. Okay. But another last doubt. In the BH curves that you did for magnetic and non-magnetic material.
Okay.
The flux is linearly increasing in the non-magnetic material. What does this logically mean, sir, with respect to that means inductance is forever changing, no, sir? It does not come to
inductance is
an
constant.
Okay.
In this case, inductance is constant, right?
Okay.
Slope. Inductance is slope.
Sir. Got it.
That will be constant at all places.
Oh, okay, sir. Yeah, got
Okay,
it.
Ashwat? Okay.
Yeah.
Pranjali. Pranjali, do you have any doubt, Pranjali?
Hello, sir. Am I audible?
Yeah, tell me please.
Sir, in case of AAC conductor, we said that the transportation is easy because of rolling,
Hmm.
and sir, their mechanical strength is low, so that's why rolling is easy.
Okay.
So, sir, that means that low mechanical strength is advantage, right?
In that way, transportation way, it's an advantage.
Okay, sir.
Wow, very simple. You have your house wire, right?
Yes, sir.
House wire you are using as a stranded.
Yes, sir.
Rather than stranded, if you are using solid,
Mhm.
definitely
Yes.
transportation of that conduct is also a bit difficult.
Yes, sir.
So in that way, stranded will be easy to transport compared to solid.
Okay. And when we try to increase the safety, so at that time we need to increase tensile strength.
You are going to compare ACSR with solid, is it?
No, sir. In AAC only.
No, by increasing mechanical strength, by adding that steel, you will say that ACSR will have a less advantage in transportation compared to AAC.
Yes, sir.
That's correct. But
Okay.
compare it to solid,
Yes, sir.
ACSR transportation is easy.
Yes, sir. Right. Yes, sir.
So in that way, we are getting advantage of transportation as well as a skin effect by going with the ACSR.
Yes, sir. Okay. Understood.
It will fall in the intermediary category. Between solid and AAC, it will fall.
Okay. Okay, sir.
Skin effect in the ACSR will be little more compared to AAC. Skin effect.
Yes, sir.
Skin
Yes.
effect in the ACSR will be more compared to AAC,
Yes, sir.
but less compared to solid.
Yes, sir. Yes, sir. Understood.
Transportation of ACSR is easy compared to solid, little difficult compared to AAC.
Yes.
So it will
Okay.
fall in that category. Okay.
Yes, sir. Okay. Thank you, sir.
Yeah. Bala Vinkesh,
Sir,
tell me.
sir, in DC2OS system, sir. Here you told total resistance is equal to RA plus RB, sir.
Yes.
It is can also be used for single phase and two-way system.
Yes. Yes.
Previous example, AC resistance should be calculated including last year. You didn't say like.
Okay, I am saying about only formula, Bala Vinkesh.
Yes.
I am commenting only on formula, not on the number, right?
Okay, okay, sir.
So if it is the AC, you take AC numbers.
Okay, sir.
Okay.
Thank you, sir.
Haripriya.
Good morning, sir.
Good morning. Tell me, Haripriya.
In the yesterday's class, why do we use hollow conductors on bus bars, sir? I mean, current rating.
To reduce corona.
Okay, sir. Sir, in current rating and radius, how they are related, sir? Hollow
Proportional. For continuous.
For high current, radius must be high, sir.
High current. If you want to send high current for a long amount of time, the radius of conductor required should be high.
How, sir?
That you should go with basic analysis of current flow.
Okay, sir.
Very simple. If you want to pass more charges, you should offer more cross section, right?
Okay, sir. Got it. Sir, other thing is how power factors are related to load, sir. Means how it increases what happens to power factor.
Power factors related to
load.
What relation you want in that power factors with load means?
I mean, what happens to the power factor when we increase the load? Means like the relation.
Actually, Haripriya, that depends upon what type of load you are adding. For example, already existing load is a resistor, something like this load. And if you add some more load extra, something like this, then power factor change might be in a different way.
Okay, sir.
Okay. But rather than this, if you add only resistive load, then again power factor will change. That change may be in a different way.
Okay.
Exactly, I can't say if the load is changing, how is the power factor.
Depends upon the load.
But one thing I'll tell you. But if you fix your element, if one load was fixed, let's say lighting load.
Yes.
Haripriya,
Yes.
we have only lighting load. I don't have any motors. Same quality of lights. Then even though you are increasing the load, power factor will not change.
Okay.
Okay.
Yes.
For example, if you have an induction motor, only one induction motor you are taking, and you are increasing the load on the induction motor. Getting me, Haripriya?
Yes, sir. Yes.
Based on that load change, power factor will change definitely.
It will lag, sir.
Lagging only, power
Lagging
factor will change.
will-
One of the simple reason, Haripriya, induction machine is over to you.
Yes, sir.
Starting power factor, full load power factor. How is that?
Low power factor.
We have a variation, right? Yes or no?
Yes, sir.
That itself is going to tell you how the power factor may change with respect to load.
Depends
But you
upon
don't
the
have a
load.
specific. You don't have a specific relation.
Okay.
Okay, it will change. It will change, but there is no specific relation.
Okay, sir. Thank you.
Okay. Yeah. Anil Kumar Malhotra.
Sir, good morning, sir.
Tell me, Anil Kumar.
Sir, leakage current, sir, that per phase equivalence.
Okay.
Explain, sir, again.
See, actually, you are applying some voltage across the insulator.
Yes, sir.
Okay.
Yes, sir.
See, after all, it's an insulator. You are applying some voltage, means voltage by that impedance. Definitely, some amount of current should flow.
Yes, sir.
Okay. But you see, this insulator body resistivity will be very, very large in number.
Yes, sir.
But surface resistivity is very low. Because it's the air, surrounding air, right?
Yes, sir.
That resistivity is low compared to insulator body.
Yes, sir.
Okay.
Yes, sir.
Because of that voltage application, definitely some small value of current will flow on the surface of the insulator according to that leakage resistance value.
Okay, sir.
Okay.
Okay, sir.
That's the leakage current what we are naming here.
Okay. Sir,
Very simple. Very simple. If you are applying some voltage across any body, is it an insulator, conductor, semiconductor, whatever it is, definitely some amount of current will flow. Is it a low or high? It depends upon the material property.
Okay, sir.
Okay.
Yes, sir. Sir, we are connecting that parallel to capacitor resistor, sir.
Yeah.
I did not get that, sir. Why we are connecting the parallel with capacitors?
Because it's a shunt element, right? Current is a shunt current.
Okay, sir.
We have to keep that as a shunt element only in our circuit.
Okay, sir. Okay.
So we have to keep that in the form of shunt.
Okay, sir. Okay. Thank you, sir.
Okay. Ramakrishna.
Yeah, hello, good evening, sir. So, sir, class is till 10 o'clock only. So,
Actually, we are arranging some more. We have some problem with the session, actually.
Okay, sir.
So I have stopped the class early.
Yes, sir.
9:20 only I
Yesterday
stopped
also,
to
sir.
spend some more time.
And even yesterday.
Yeah. We have some platform problem. That's why it's getting disconnected just after 10. There is some other class.
Okay, sir.
We will try to rectify it. Okay. Yeah, tell me, Ram.
Yes, sir.
What's your
So, one general doubt, sir. So, in 4 or 5 years down the line, we were using 60-watt bulb, no, sir. So, if we continuously turn off and on for many times, it will get off after some days. So, it is due to switching over voltage or why it is so?
Switching over voltage effect will not be there on the incandescent bulb at all.
Okay.
Because it is a resistor.
Okay, sir.
So switching effect will not be there. But why it is getting damaged in the sense because of excessive heat, long usage. Actually, you tell me, Ramakrishna,
yes, sir.
Life of a bulb measured in what?
Measured in
Life of
losses how much it is?
No. Life of a man is measured in days, months, years.
Yes, sir. So in time, yes.
Similarly, life of a bulb is measured in hours.
Yeah, hours.
Working hours.
Yes, sir.
Okay. So if that is getting exhausted, bulb may survive or may damage.
Okay, sir.
According to our usage only. Even if you want If you are purchasing some LED lamp or something,
Yes, sir.
just
They
see.
also have, yes, sir. I mean, hours.
They will write. They will write.
Yes, sir.
These many number of hours it will survive.
Yes.
Okay.
Yes, sir. So another doubt, sir, in desirable characteristics of transmission line, you said that line has it should have minimum voltage drop. So if
No,
it
I
doesn't,
don't say it should have minimum voltage drop.
no, it should low as possible. We should make it as low as possible.
Actually, line will consist of voltage drop.
Yes,
I have
sir.
to maintain that value as low as possible.
Low as possible. So if
Because
we
I
don't
can't make
maintain,
it zero. I
yes,
can't
sir,
make
yes,
it
sir.
zero.
Okay.
Okay.
Yes, you said that if we don't maintain the VR, after if VR has less voltage than VS, after some time it will get off.
Not off.
There is a
actually,
more
load performance will be definitely affected because of the low voltage.
Yes, sir. But still, we can't reduce everything, no, sir. So after some time, it may even after some time it may get stopped.
No, I didn't get you. Can you please repeat?
So even after making voltage drop in line as low as possible, it will be less than VS, no, sir. Source voltage.
Maybe yes.
So
you keep that VR in your range.
Okay. So okay.
Keep that VR in your range.
Okay. Yes, sir. And why you have written that positive sequence before RLC, sir?
Because we are considering only ABC sequence analysis here.
We are taking it as positive sequence voltages, so we have taken
balanced
voltages. Yes, sir. Okay, yes. Okay, that's it. Thank you.
Yeah. Akshay.
Hello, sir. Am I audible?
Tell me, Akshay.
Sir, in ACSR conductor, you mentioned that the central conductor, there would be less current flowing through it. So, yeah, so why is that, sir? Due to skin
effect only. Skin effect only.
But earlier you mentioned that, like,
even AAC also, internal strand will carry very less amount of current.
Sir, is it like can you take the last slide when you explained ACSR? Yeah.
This one?
This one, yes, sir. Sir, in that central conductor, how will the current flow? Like
very less, maybe red, very less.
Okay, so why, sir, in the center? So is it like a combined effect or?
Combined effect only. Definitely, one strand will show its effect on the other strand.
Okay, so
mutual effect will also be there in that current flow.
Okay, sir. Okay, sir. Sir, then like in the composite conductor, like between the adjacent conductors, will there be current flow because they are connected to
the composite conductor between
the different strands, will there be current flow?
One strand to other strand, you are asking?
Yeah. Yes, sir. Yes, sir.
All are operating at same voltage, right?
Yeah, but yeah,
so overall it's a conductor for us. You may not have a jumping of current from one strand to other strand because all are shorted first of all. Getting?
Yeah. Okay. Sir, then
all the strands will try to divide the current input.
Okay. Yeah. That makes sense. Yes. Sir, then one more thing, that in DC one-wire system, we took the area perpendicular to current flow direction as pi r square, but that is perpendicular only at the time that it enters into the ground, right? After that, it flows in a different direction. No?
Any direction it will flow. Earth looks to be circular only. Huh?
Like if it
any direction it is flowing, doesn't matter.
Like if the current is flowing through the surface, then it won't be circular, right? No, sir.
We will be keeping that electrode deep down. The earth electrode, we don't say just on the surface of ground. Even if we keep just on the surface of ground, current will not flow.
Okay. Oh, yes.
Because the resistivity issue is there again.
Okay.
So for a better grounding, we should go for a deep length. Then only we can get it.
Approximately, yes, sir. Okay. Sir, then one thing, like last class you mentioned that in bus bar we use hollow conductors so that this corona effect would be reduced, but like in distribution system we use ACR. So from where this ACR gets converted into hollow, or in real life we don't use hollow?
In real life we don't have in India. That's fine.
Oh, okay. Sir.
We don't have that in India. Some foreign countries, they are using it. to reduce corona.
Okay, sir. Sir, then what is the difference between operating voltage and rated voltage?
What's the rated voltage of your house?
220 volts, like single phase.
230?
230.
You have panel board in your house
Yes, sir.
or in your apartment?
Yes, sir. Yes.
How much voltage it will show?
Around the same, kind of.
Variations are there continuously.
Yeah, slight. Yeah, variations are there.
That's the operating voltage.
Okay. Okay, sir.
But whatever you said, 230 or 220, that is the rated voltage. What you are saying. Rated voltage is a voltage at which your apparatus are designed to work.
Okay, and operating is what you are getting actually.
What we are getting in practice.
Okay.
Regularly,
Sir,
continuously.
okay. Sir, then one more doubt, sir. Positive sequence and balance, I didn't get it, sir.
Have you attended FNS?
No, sir.
It will be simply balanced system, ABC sequence you assume for time being.
Okay.
Positive sequence is ABC phase sequence. Okay?
Okay.
ABC phase sequence. Yeah?
Okay, sir. Okay, sir.
Any other doubt you have, Akshay?
No, no, sir. Nothing else. Thank you, sir.
Fine. Vishnu.
Sir, it's regarding one of the doubts. Somebody asked that if you reduce this conductor size to skin depth. Hello.
Tell me.
If you reduce the size to skin depth, you said that the skin, the entire skin effect would be reduced. If you look at that, even if you reduce the size again, that small contour also you will have skin effect, no, sir?
No, that's what he said, right? You are reducing the radius of conductor to skin depth.
The
radius of
reducing
conductor equals.
Okay. We're reducing it to skin depth, not by skin depth.
Not by skin depth, to skin depth.
Okay.
They are making very thin
Sir.
conductor. Very thin conductor.
Okay, sir. Then its current rating will be very much low, no, sir?
Then you have to bunch number of strands.
Oh, okay, sir.
To make up the required current rating.
And sir, in this regarding this last thing you explained about this inductance. You said that if it is a magnetic material in between, then it will be a non-linear inductor. So in the case of ACSR, then will it be a non-magnetic because you have steel, galvanized steel inside?
Very less non-linearity you will have.
Because the current going through it is very much low.
Yes. You can neglect, you can say.
And sir, regarding this measurement of R, that you said that we measure it using this. You supply in some power, you calculate the output power. From the losses you can calculate R, sir.
Yes.
So then in measurements there are something called this bridges, AC bridges. So if you take some unit length, like say some around 1 meter, if you take and if you use an AC bridge and calculate the resistance into that proportionate length, that will also give RAC, no, sir?
You are thinking about AC bridge.
Because
okay, you can do that also.
There also you have 50 hertz supply. Skin effect
go
also.
For low resistance method.
Yes, sir.
Low resistance method we have to use. Low resistance AC bridge, anything you have?
Low resistance, sir, all those
Kelvin's double bridge. Kelvin's double bridge is for AC or DC?
Kelvin's is for low resistance. I think it's DC only, sir. AC, those Maxwell inductance.
AC, you think about only inductance and capacitance calculations.
Yes, sir.
Resistance calculation, they will use only DC bridges.
Yes, sir.
Instead of DC supply, if you give AC supply. Or Kelvin's double bridge or anything.
So, but again, Kelvin's is used for extremely low resistance. That is around decimals point.
That's needed, right? That's needed, no?
Oh, for exact precise values.
1 meter wire you are taking.
Oh, length is low. Okay.
Very, very low resistance you get, maybe in milliohms.
So that if you multiply into required, like for instance, if I want 1 meter means
for lumping.
For
lumping.
Okay. And sir, last thing is
1 kilometer might have 0.1 ohm resistance, approximately.
Okay.
So 0.1 by 1000 you have to take for 1 meter. So 0.1 milli.
Then okay, Kelvin's only is correct. And sir, then last thing, one more thing is you did mention in between that this ACSR would have a skin effect that lies between the solid and that of the AC.
Yes. Because
That is
of
because of the
steel.
fact that the
Steel.
doesn't carry any current, so effective area reduces.
Magnetic material we have introduced. No, μr was increased.
Oh, okay. That's so we can also say by this logic, sir, this area effective area gets reduced. Okay, sir. That one, okay. Then this current, sir, in DC single phase regarding this ground current, similarly to somebody else. Sir, if this conducting ground, for instance, is like an extremely dry area, maybe like a desert, we are setting up this plant.
Then you have to go for low depth.
Till we have some moisture.
Yeah. See, even HVDC stations are grounded at a depth of half kilometer.
Oh.
Half kilometer they will drill.
Oh, okay.
So there they will keep the electrode for a perfect grounding, because they have to run current of kiloamperes.
Okay, sir.
In the ground. So they will go up to that depth.
All right. So then regarding another one is this power, this stability, sir. There is just one thing. So this entire thing in this we model this entire power system into like one generator which we want to study and one single machine infinite bus. Everything whatever we study was converting this thing into an SMIB form.
Yeah.
So this so why are we converting SMIB, sir? We are considering this infinite bus as the power system and the generator
Because
to be studied.
doing stability analysis on a multi-machine system is laborious for us right now.
Yes, sir.
So on what machine you want to do stability analysis, concentrate only on that machine.
Okay, and isolate the rest as a infinite bus.
Infinite bus, yes.
All right, sir. All right, sir. Thank you, sir.
Yeah. Sachin.
Hello.
Tell me, Sachin.
Sir, in this, how we got that stray capacitance and line capacitance?
See, generally, capacitance conditions, I said, no, two conducting bodies.
Yeah.
Dielectric material between them, voltage gap.
Sir, explain in figure, because some network issue occurs at that time.
Yeah, okay. See, I'll write. Conditions for the formation of capacitance. For capacitance formation, okay?
Okay.
At least two conducting bodies, first condition. Two conducting bodies should exist. Next, there should be a dielectric material between them. Dielectric between them, okay?
Okay.
And last condition, there should be some potential gap. There should be a potential gap between the bodies. Between conducting bodies, okay?
Okay.
If that is satisfied between ground and conductor, is it satisfied?
Yeah, there is air is insulation.
Conductor, ground and what you call power conductor. Between that, we have a potential gap of phase voltage.
Yeah, two phase.
Then definitely capacitance will be formed.
Okay. This is line capacitance.
Line to ground, and then line to line also we have a line to line voltage gap, right?
Okay.
Clear?
Yes, sir, clear. And inductor is also like that only, na?
Inductor, just if you have a current flow in a conductor, that is sufficient. It will produce a magnetic flux linkages. It will have its inductance.
Thank you, sir. Got it.
Yeah. Datri. Daritri.
Hello, sir.
Tell me.
Sir, how to reduce the skin effect in the SCR conductor?
ACSR, sir.
Sir, SCR.
No, already we have reduced the skin effect from solid to ACSR. Beyond the ACSR, reducing skin effect may not be possible.
Sir, how to reduce?
In what? In what material?
Sir.
Behera, tell me what's your doubt exactly.
Sir, my doubt is ACSR conductor.
Okay.
Skin effect in there, na?
Skin effect we can't make zero.
Sir, kiss?
Yeah.
The solid conductor, skin effect in there.
Solid conductor, skin effect is very high.
Yes, sir.
Okay, to reduce it only, we are moving to stranded conductors.
Oh, yes, sir.
But beyond stranded conductors, reducing skin effect may not be economical.
Yes, sir.
So to reduce the skin effect to a very, very low level, we have to make the strand size very, very thin. Okay,
yes, sir.
that's why
Yes, sir.
we are going up to some extent and we are leaving it.
Yes, sir.
We are not making it as zero.
Yes, sir. Sir, one more doubt is last class. Sir, what is source voltage?
What is?
Source voltage.
Surge voltage, it's a over voltage only. Surge voltage, over voltage, transient voltage, all the terms are same, Behera.
Yes, sir.
Yeah.
Thank you, sir.
That's it?
Yes, sir.
Okay, fine. Tulsi.
Hello, sir.
Tell me, Tulsi.
Sir, current perpendicular direction of such a
No, current is flowing on the surface of ground.
Yes, sir.
We have to measure the area perpendicular to the direction.
Yes, sir.
So you have to look into the ground like this.
Hello, sir.
You have to look into the ground, right?
Yes, sir.
If you are looking into the ground, how that ground looks to be for you? Circle.
Yes, sir.
Then it's a circular cross section.
Okay. Okay, sir.
Okay?
Yes, sir. Sir, that star delta conversion CAN.
Yeah. Tell me.
I am not getting it, sir. Means we want to convert the delta to star.
Yeah, actually, we have to get only effective capacitance from a phase A conductor.
Yes, sir.
So these three capacitance are there, but we have a line-to-line voltage across each capacitance.
Yes, sir.
But we need a capacitance which will experience only per phase voltage.
When we convert it into delta star, we are getting the line to line now, sir.
No, A to neutral, B to neutral, C to neutral you get, right?
Okay, okay. Okay, sir.
This is the A to neutral capacitance.
Okay.
Clear?
Yes, sir.
Any other doubt you have, Tulsi?
74F, sir. In previous.
Tell me what's that point you have there?
Sir, is it practically possible? I am asking.
Which one?
I too didn't note it, sir, but just I noted the page number.
No, you just read what you have written in that page number.
Sir, actually, due to network issue, I didn't take the snapshot also, sir.
Okay. What's the 73rd page?
73. 1 minute.
Okay, you try to search it where you have?
No, sir. That's. Thank you, sir.
Yeah. Karthik.
Hello, sir. Am I
Tell me,
audible?
Karthik. Yeah.
Sir, regarding the HVDC transmission, we are using bipolar and unipolar, sir.
Yeah.
Sir, in unipolar, we are only using single conductor. So means it would be economical. It would be more economical than bipolar, right, sir? In bipolar,
But, we have some issues of ground current and all.
Okay, sir.
The monopolar, you have to circulate 100 kiloamperes of current in the ground.
So we have to
that is disturbing various communication signals, railway signals, causing for some induced EMFs in the water pipes, what we lay in the ground.
Okay, sir.
Okay, those issues
So-
will be there. That's why we don't suggest to go for monopolar link.
Yes, sir.
Okay.
That's it, sir.
That's it.
Okay, yes, sir.
Yeah. Sign on.
Sir,
Tell me, sign on.
regarding DC one wire system, sir. The once you explain that A equal to pi R E square.
That's what I have explained till now. We have a current flow in the ground.
Sir.
Okay. We have to measure the area perpendicular to the direction of the current flow.
Okay, sir.